When you look at thousands of unlabeled data points scattered across a high-dimensional feature space, you are staring at one of the most fundamental challenges in modern machine learning. In supervised learning, every data point comes with a ground truth label guiding the model toward a known target. But in the vast majority of real-world scenarios, data arrives without labels, without metadata, and without an explicit playbook. Consider a massive payment processing engine attempting to detect anomalous fraudulent behavior among millions of daily transactions, or a global e-commerce platform trying to discover organic customer personas without predefined categories. In these environments, the system must discover structure entirely on its own. This is the realm of unsupervised learning, and at the heart of unsupervised learning lies the challenge of clustering. Clustering is the process of grouping data points such that objects within the same group share greater similarity with one another than with objects assigned to other groups. At first glance, grouping similar items together seems intuitively trivial to human perception. If you look at a two-dimensional scatter plot featuring three distinct visual clusters of dots, your visual cortex instantly segments the space, identifying the boundaries and centers of those groups within milliseconds. However, when those data points expand into dozens, hundreds, or thousands of continuous dimensions, human visual intuition vanishes completely. We cannot visualize a 784-dimensional space, nor can we draw visual boundaries across complex hyperplanes. Machine learning algorithms must therefore replace visual intuition with rigorous mathematical definitions of distance, variance, and density. Among all clustering techniques, the k-means algorithm stands as the most widely used, heavily studied, and foundational partitioning method in data science. To build a robust mental model of k-means, imagine a vast physical warehouse where thousands of packages arrive on a conveyor belt. Each package has specific physical attributes, such as weight, height, depth, and destination region. Your goal as a system architect is to set up a fixed number of sorting stations, denoted by the letter K, throughout the warehouse floor. You want to place these K sorting stations in locations that minimize the total distance every package must travel from the conveyor belt to its nearest assigned station. If you place a station too far away from a heavy cluster of packages, workers waste immense energy transporting those items across the floor. If you position the stations precisely in the geometric center of major package concentrations, total transport effort is minimized. This physical warehouse setup represents the core objective of the k-means algorithm. In mathematical terms, k-means attempts to partition a dataset of n observations into k distinct, non-overlapping clusters, where each observation belongs to the cluster with the nearest mean. This geometric center of a cluster is known as a centroid. The centroid is not necessarily one of the original data points from your dataset. Rather, it is a synthetic point representing the arithmetic mean of all feature vectors currently assigned to that cluster. If your feature space has 50 dimensions, each centroid is itself a vector of 50 continuous values, sitting at the calculated center of mass for its assigned cluster. To understand how k-means achieves this partitioning, we must examine its objective function, known as the within-cluster sum of squares, or inertia. Imagine measuring the straight-line Euclidean distance between every single data point and its assigned cluster centroid, squaring those distance values, and summing them up across all data points in the dataset. The result is a single scalar number representing the total variance or dispersion within the clusters. The mathematical goal of k-means is to find a set of k-centroid positions and a set of cluster assignments that minimizes this within-cluster sum of squares. Squaring the Euclidean distance is a deliberate mathematical choice. By squaring the distances, the algorithm penalizes points that are far away from their centroids much more heavily than points that are already close, forcing centroids to move toward regions that accommodate outliers and distant points efficiently. The optimization process of k-means operates through a simple yet powerful iterative algorithm known as Lloyd's algorithm, or expectation maximization in a discrete setting. The algorithm begins by selecting initial locations for the k-centroids. Once initial centroids are placed, Lloyd's algorithm alternates back and forth between two core steps until convergence: the assignment step and the update step. In the assignment step, the algorithm fixes the current locations of all k-centroids and iterates through every data point in the dataset. For each data point, it calculates the Euclidean distance to all k-centroids and assigns the point to whichever centroid is closest. This step effectively partitions the entire feature space into Voronoi cells, where every point in space belongs to the region governed by its nearest centroid. Once every data point has been assigned to a cluster, the algorithm transitions to the update step. In the update step, the cluster assignments are held fixed, and the location of each centroid is recalculated. The algorithm takes all data points currently belonging to cluster 1 and computes their component-wise average across every feature dimension, moving the centroid vector to this new mean position. It repeats this calculation independently for all k-centroids. Because the new centroid position is the exact geometric mean of its assigned points, this relocation guarantees that the within-cluster sum of squares for each individual cluster is either decreased or stays exactly the same. The algorithm then loops back to the assignment step, reevaluating which centroid is closest to each point based on the updated centroid locations. This alternating loop between assignment and update continues continuously. As centroids shift, some data points on the boundary between clusters switch their allegiance from one centroid to another. These reassignments cause the centroids to shift slightly again in the next update step. However, because the total within cluster sum of squares strictly decreases or remains constant at every single step, and because there are only a finite number of ways to partition n data points into k-clusters, Lloyd's algorithm is guaranteed to converge. Convergence occurs when no data points change cluster assignments during an assignment step, meaning the centroid locations remain perfectly stationary from one iteration to the next. From a mathematical optimization perspective, Lloyd's algorithm can be proven to be a coordinate descent optimization procedure on the inertia cost surface. In the expectation or assignment step, coordinate descent optimizes the discrete cluster assignment variables while holding centroid vectors constant. In the maximization or update step, coordinate descent optimizes the continuous centroid vectors while holding discrete cluster assignments constant. Because both coordinate descent steps non-increase the continuous inertia function bounded below by 0, local convergence is mathematically guaranteed. Despite its mathematical guarantee of convergence, k-means suffers from a critical vulnerability. It is an iterative local search procedure, meaning it is not guaranteed to find the global minimum of the objective function. The final clusters discovered by k-means depend heavily on the initial positions chosen for the centroids at the very start of the algorithm. If initial centroids are placed by bad luck in poor starting locations, such as putting two centroids right next to each other inside a single natural cluster while leaving another distinct cluster without any centroid nearby, the algorithm will get trapped in a suboptimal local minimum. The centroids will settle into local equilibrium, producing arbitrary cluster boundaries that fail to reflect the true underlying structure of your data. Historically, the simplest approach to initialization was random initialization, where the algorithm selected k data points at random from the dataset to serve as the initial centroids. However, pure random initialization is notoriously unreliable, often requiring hundreds of random restarts to chance upon a good clustering configuration. To solve this fundamental flaw, researchers developed K-means++, a smart initialization algorithm that places initial centroids far apart from one another before Lloyd's algorithm even begins. Imagine placing your first centroid by selecting one data point entirely at random from your dataset. To choose the second centroid, you do not select at random. Instead, you calculate the distance from every remaining data point to that first centroid. You then select the second centroid using a probability distribution where the probability of picking any given point is proportional to the square of its distance from the first centroid. A point that is very far from the first centroid has a high probability of being chosen, while a point close to the first centroid has almost zero probability. For the third centroid, you compute the distance from every point to its nearest existing centroid, square those distances, and sample again according to that weighted probability distribution. You repeat this probabilistic selection until all k initial centroids are chosen. By forcing initial centroids to spread out across the feature space, K-means++ drastically reduces the likelihood of placing multiple centroids inside the same natural cluster. Theoretical proofs demonstrate that K-means++ guarantees an expected upper bound on the final within-cluster sum that is logarithmic in the number of clusters, providing both faster convergence speed and significantly higher clustering quality compared to random initialization. In modern production machine learning libraries, K-means++ is the default initialization strategy. Beyond initialization, engineers must contend with the fundamental structural assumptions embedded within the K-means algorithm. K-means assumes that clusters are spherical, convex, and roughly equal in variance and size across all feature dimensions. This assumption stems directly from the use of isotropic Euclidean distance in the objective function. Euclidean distance treats every direction in space equally. If your natural clusters are shaped like elongated ellipses, crescent moons, intertwined rings, or continuous density manifolds, K-means will fail dramatically. It will cut elongated clusters in half and forcefully group points based on straight-line geometric proximity rather than structural continuity. Furthermore, K-means is extremely sensitive to feature scaling. Imagine clustering customer data where one feature is age, ranging from 18 to 80, and another feature is annual income, ranging from $20,000 to $2 million. If you calculate Euclidean distance on these unscaled raw numbers, a difference of $10,000 in income will completely swamp a difference of 50 years in age. The algorithm will effectively ignore age entirely, treating income as the sole dimension of variation. To prevent this pathology, feature normalization, such as standard scaling to zero mean and unit variance or min-max scaling, is an absolute mandatory prerequisite before running K-means. Another major limitation of standard K-means is its sensitivity to extreme outliers. Because the objective function squares the Euclidean distance between points and centroids, a single extreme outlier sitting far away in feature space exerts an enormous gravitational pull on the nearest centroid. The centroid will shift dramatically away from the dense core of valid data points just to minimize the massive squared error contributed by that single distant outlier. In severe cases, an outlier can even capture its own dedicated cluster centroid, wasting valuable model capacity. When dealing with noisy datasets containing heavy outliers or when operating in non-Euclidean metric spaces, system architects often turn to k-medoids, also known as partitioning around medoids or the PAM algorithm. Unlike k-means, where centroids are synthetic mean vectors, k-medoids restricts every cluster center to be an actual real data point from the dataset called a medoid. Furthermore, instead of minimizing squared Euclidean distances, k-medoids can minimize arbitrary distance metrics, such as Manhattan distance, cosine distance, or domain-specific dissimilarity measures. To visualize k-medoids, consider choosing an actual representative customer from your dataset to serve as the benchmark center for a customer segment, rather than computing an artificial average customer vector with fractional attributes that no real human possesses. During each iteration of partitioning around medoids, the algorithm evaluates candidate swaps between current medoids and non-medoid data points. If swapping a current medoid with a non-medoid point reduces the total sum of dissimilarities across the dataset, the swap is executed. Because medoids use absolute dissimilarities rather than squared distances, an extreme outlier point does not disproportionately distort the cluster center. The medoid remains anchored firmly within the dense bulk of representative points. However, this robustness comes at a heavy computational cost. Standard k-medoids algorithms scale quadratically with the number of data points, making them computationally prohibitive for massive datasets without sampling optimizations like Clara or Clarence. For high-throughput, large-scale industrial applications where datasets contain millions or billions of feature vectors, even standard Lloyd's k-means can become a bottleneck due to its requirement to scan the entire dataset during every single assignment step. To overcome this memory and compute limitation, mini-batch k-means provides an approximate optimization approach. Instead of using the full dataset to update centroids at each step, mini-batch k-means draw small, random subsamples or mini-batches of data points that fit comfortably in memory. In mini-batch k-means, for each incoming mini-batch, data points are assigned to their nearest existing centroids. Then, centroids are updated using a smooth online sliding average step, moving slightly toward the mean of the mini-batch points. By iterating over mini-batches sequentially, the centroids converge rapidly toward optimal positions in a fraction of the time required by full-batch k-means. While mini-batch k-means produces slightly higher within-cluster sum of squares inertia than standard k-means due to stochastic sampling noise, the quality reduction is usually negligible compared to the massive order-of-magnitude reduction in execution time and memory footprint. Another important variation is k-medians. While k-means calculates cluster centers as the arithmetic mean using L2 squared Euclidean distance, k-medians calculates cluster centers as the spatial median along each feature dimension using L1 Manhattan distance. By minimizing the sum of absolute errors rather than squared errors, k-medians achieves exceptional resistance to severe extreme outliers, providing a computationally efficient alternative to full k-medoids when operating under Manhattan metric spaces. To combine the scalability of partitioning methods with the structural flexibility of hierarchical splitting, engineers use bisecting k-means. Bisecting k-means begins with all data points in a single master cluster. It then repeatedly selects the cluster with the highest internal variance and splits it into two subclusters using a standard two-means k-means step. This binary splitting recurses until the target cluster count k is reached. Bisecting k-means is less sensitive to initial centroid placement than standard k-means and produces clean, hierarchical binary cluster trees with linear time scaling. When hard cluster assignments are too rigid for overlapping data boundaries, engineers turn to fuzzy C-means or soft K-means. In standard K-means, every data point belongs exclusively to one cluster, yielding a binary membership coefficient of 0 or 1. In fuzzy C-means, each point maintains a continuous degree of membership across all K clusters, represented as probabilities that sum to 1. A customer sitting right on the boundary between budget shoppers and premium buyers receives a 50% membership probability in both segments rather than being forced into a single bin. The cluster centers in fuzzy C-means are calculated as weighted averages, where each point's contribution is scaled by its fuzzified membership score raised to an exponent parameter m. As m approaches 1, fuzzy C-means converges back to hard K-means. As m increases, cluster boundaries become softer and more overlapping. Another specialized variation is spherical K-means, designed specifically for high-dimensional directional data like normalized text document embeddings or TF-IDF feature vectors. Standard Euclidean K-means measures spatial distance, which suffers in high-dimensional sparse spaces where vector length varies wildly based on document length. Spherical K-means replaces Euclidean distance with cosine similarity, projecting all feature vectors onto a unit hypersphere. During the assignment step, data points are assigned to the centroid with which they share the maximum cosine angle. During the update step, centroids are calculated as the vector sum of assigned points and subsequently renormalized to unit length. This directional clustering ensures that text documents are grouped according to their semantic content rather than word count volume. For online streaming environments where data arrives continuously in real-time message streams, engineers employ online streaming K-means, such as McQueen's streaming algorithm. Instead of storing historical data in memory, McQueen's algorithm updates centroid locations incrementally for every single incoming vector, adjusting the centroid position inversely proportional to the total number of points assigned to that cluster so far. This provides zero memory footprint clustering over infinite data streams. System engineers must also configure convergence tolerance settings carefully during implementation, rather than waiting for absolute zero centroid movement, which can cause endless microiterations due to floating point imprecision. Production implementations define a relative tolerance threshold, delta. Convergence is declared when the Frobenius norm of the shift in centroid vectors between consecutive iterations falls below delta times the overall variance of the dataset. Setting delta too high halts training early in suboptimal configurations, whereas setting delta too low causes unnecessary CPU cycles on micro-adjustments that have zero structural impact on cluster membership. From a computational complexity perspective, a single iteration of standard full-batch Lloyd's algorithm requires calculating the distance between n data points and k centroids across d feature dimensions, yielding a time complexity of big O of n times k times d per iteration. If the algorithm takes I iterations to converge, total time complexity is big O of n times k times d times I. Space complexity is remarkably lightweight, requiring big O of n plus k times d to store data points, feature vectors, and current centroid locations in memory. This linear scaling with respect to the number of data points makes K-means significantly more scalable than hierarchical or density-based clustering techniques, cementing its position as the first-line algorithm for large-scale exploratory data analysis. When implementing K-means in modern software architectures, engineers must explicitly manage several operational edge cases. First is the problem of empty clusters. During iteration, it is mathematically possible for a centroid to lose all of its assigned data points if other centroids move closer to those points. If a cluster becomes empty, Computing its new mean in the update step results in a division by zero error. Robust implementations detect empty clusters during the update phase and automatically reinitialize the orphan centroid, typically by placing it at the location of the data point that currently exhibits the highest individual squared error from its assigned centroid. Second is the determination of the parameter k itself. Standard k-means does not learn the number of clusters automatically. K is a hyperparameter that must be specified prior to execution. Choosing K requires balancing mathematical metrics with operational interpretability, a challenge we will explore deeply when analyzing evaluation metrics. In summary, K-means is an efficient, scalable, centroid-based partitioning algorithm that minimizes the within-cluster sum of squares through iterative expectation maximization. Its performance relies on effective feature normalization, thoughtful initialization using k-means++, and an awareness of its geometric assumption of spherical clusters. When its assumptions hold, k-means delivers fast, intuitive, and highly actionable cluster structures across massive continuous datasets. When non-spherical geometries, complex metric spaces, soft boundaries, or heavy outliers dominate, variants like k-medoids, k-medians, bisecting k-means, fuzzy c-means, spherical k-means, or alternative paradigms like hierarchical and density-based clustering provide essential alternatives. While partitioning methods like k-means force a dataset into a flat, non-overlapping collection of k-groups, many real-world systems exhibit structures that are naturally nested and multiscale. Consider an organizational chart of a global software enterprise, where individual software engineers belong to small feature teams belong to engineering departments belong to regional business divisions, and divisions belong to the overarching corporate entity. Or consider biological taxonomy, where individual organisms are grouped into species, genera, families, orders, classes, phyla, and kingdoms. In these domains, forcing data into a single fixed number of clusters destroys the rich, multi-tiered relationships embedded within the system. To discover and capture these multi-scale relationships, we turn to hierarchical clustering. Hierarchical clustering constructs a nested hierarchy of clusters represented visually as a binary tree, called a dendrogram. Unlike k-means, hierarchical clustering does not require you to specify the number of clusters k prior to execution. Instead, the algorithm builds a complete spectrum of clusterings, ranging from a configuration where every single data point sits in its own isolated individual cluster, all the way up to a single master cluster containing every data point in the entire dataset. Once the hierarchy is constructed, an engineer can slice the dendrogram horizontally at any height threshold to extract the precise granularity of clustering required for a given operational workload. Hierarchical clustering operates primarily under two distinct architectural paradigms: agglomerative hierarchical clustering and divisive hierarchical clustering. Agglomerative clustering is a bottom-up approach. It begins at the leaves of the tree, treating every data point as an independent singleton cluster. At each iteration, the algorithm scans the entire set of available clusters, identifies the two clusters that are most similar according to a chosen metric, and merges them together into a single combined cluster. This merging process repeats step by step until all data points are unified into a single root cluster. Divisive clustering, on the other hand, is a top-down approach. It starts at the root of the tree with all data points contained in a single giant cluster and iteratively splits the most heterogeneous cluster into two smaller subclusters until every point reaches isolation. To understand divisive clustering in technical detail, consider the Diana algorithm, which stands for divisive analysis. Diana begins with all observations in one large cluster. At each stage, the algorithm identifies the cluster with the largest diameter, defined as the maximum dissimilarity between any pair of points within that cluster. It then selects the point within that cluster that has the highest average dissimilarity to all other points in the cluster to seed a new splinter group. In subsequent steps, other points from the main cluster are evaluated to see if they are closer on average to the splinter group than to the remainder of the original cluster. If so, they are reassigned to the splinter group. This splitting procedure recurses down the hierarchy. Because evaluating every possible binary split of a cluster of size n requires checking 2 to the power of n-1 combinations, divisive algorithms rely on greedy heuristic splits, such as running local two-means partitioning or principal component projections at each node. Despite these heuristics, divisive clustering remains computationally demanding, which is why bottom-up agglomerative methods dominate industry production pipelines. To understand how agglomerative hierarchical clustering operates under the hood, we must examine the concept of distance matrices and linkage criteria. The algorithm begins by constructing a pairwise distance matrix between all n data points in your feature space. If you have 10,000 observations, the distance matrix is a 10,000 by 10,000 symmetric grid storing the calculated dissimilarity between every pair of points. The distance between individual data points can be measured using various metric spaces. Euclidean distance measures straight-line spatial distance. Manhattan distance, or L1 norm, measures distance along grid axes, making it suitable for high-dimensional spaces or sparse data. Cosine distance measures the angle between feature vectors, ignoring magnitude variations. Mahalanobis distance accounts for correlations between feature variables by incorporating the empirical covariance matrix, effectively stretching and warping space to reflect variable dependencies. Once the initial distance matrix between individual data points is computed, the first merge is straightforward. The algorithm merges the two closest points. However, as soon as a cluster contains two or more points, a critical mathematical challenge emerges. How do you measure the distance between a single point and a multi-point cluster, or between two multi-point clusters? This is the core problem of linkage criteria. A linkage criterion is a mathematical rule that defines the dissimilarity between two sets of data points based on the pairwise distances between their individual constituents. To update distance matrices efficiently after each merge event, high-performance algorithms utilize the Lance-Williams recurrence formula. The Lance-Williams formula provides a unified mathematical expression for updating the distance between an existing cluster K and a newly merged cluster formed by combining clusters I and J. By adjusting parameters alpha I, alpha j, beta, and gamma within the Lance-Williams formula, the exact distance update logic for single linkage, complete linkage, average linkage, McQuitty linkage, median linkage, centroid linkage, and Ward's linkage can be computed in constant big O of 1 time per candidate pair, avoiding raw pairwise distance recomputations. The primary linkage criteria used in software engineering each impose a distinct geometric bias on cluster formation, dramatically altering the topology of the resulting tree. Single linkage, also known as minimum linkage or nearest neighbor linkage, defines the distance between two clusters as the absolute shortest distance between any single point in the first cluster and any single point in the second cluster. Imagine two islands separated by a narrow ocean channel. Single linkage measures the distance between the two islands by finding the two closest shorelines. Because single linkage only requires a single close pair of points to justify merging two clusters, it excels at discovering arbitrary, non-spherical, continuous thread-like shapes. However, this defining property introduces a severe structural pathology known as the chaining effect. If a sparse line of noisy background points stretches between two large, distinct, dense clusters, single linkage will follow the chain of individual close points like a line of stepping stones, prematurely merging the two massive clusters into a single sprawling blob. Complete linkage, also known as maximum linkage or furthest neighbor linkage, represents the exact polar opposite of single linkage. Complete linkage defines the distance between two clusters as the absolute maximum distance between any single point in the first cluster and any single point in the second cluster. Returning to the island analogy, complete linkage measures the distance between two islands by finding the 2 points on opposite far shores that are furthest apart from each other. Before complete linkage will merge two clusters, every point in the first cluster must be relatively close to every point in the second cluster. As a result, complete linkage completely eliminates the chaining effect, resisting noise bridges and producing compact, tightly bound, spherical clusters with roughly equal diameters. However, complete linkage is extremely sensitive to outliers. A single distant outlier point at the edge of a cluster inflates the maximum distance calculation dramatically, preventing two otherwise highly similar clusters from merging. Average linkage, also known as the unweighted pair group method with arithmetic mean, provides a balanced compromise between the extreme optimism of single linkage and the extreme pessimism of complete linkage. Average linkage defines the distance between two clusters as the arithmetic average of all pairwise distances between every point in the first cluster and every point in the second cluster. To compute average linkage distance, the algorithm sums up the distances between every possible pair of cross-cluster points and divides by the total number of cross-cluster pairs. By taking the average across all constituent pairs, average linkage accounts for the overall density and structural distribution of both clusters. It is far less sensitive to single outlier points than complete linkage and entirely immune to the chaining effect that plagues single linkage, making it a robust default choice for general-purpose hierarchical data analysis. McQuitty linkage, also known as weighted pair group method with arithmetic mean, simplifies average linkage updates by taking the unweighted mean of the distances from the candidate clusters to the target cluster during merges. Centroid linkage measures the distance between the geometric centroids of two clusters, though it can introduce non-monotonic inversions where merge heights decrease in later iterations. Median linkage uses the geometric median between merged cluster centers to prevent single-point distortions. Ward's linkage, or Ward's minimum variance method, approaches cluster merging from an optimization perspective similar to k-means. Instead of measuring spatial distances between cluster boundaries, Ward's linkage calculates how much the total within cluster sum of squares variance would increase if two candidate clusters were merged into one. At each iteration, Ward's linkage merges the specific pair of clusters that minimizes the growth of internal variance. To visualize Ward's linkage, imagine each cluster as a physical object with a center of mass and a rotational moment of inertia. Merging two small, dense clusters that sit close together adds very little variance to the system, whereas merging two distant or spread out clusters causes a massive surge in total variance. Because Ward's linkage explicitly optimizes variance reduction, it naturally generates dense, highly compact, well-separated spherical clusters of similar sizes, mirroring the objective of k-means while preserving full hierarchical relationships. As the agglomerative algorithm iterates through successive merges, it records each merge event, the two participant clusters, and the exact linkage distance at which the merge took place. This historical log forms the foundation of the dendrogram. In a dendrogram, the horizontal axis typically represents individual data points or leaf nodes, while the vertical axis represents the merge distance. Vertical lines connect merging clusters, and the height of the horizontal bar connecting two branches reflects the distance between those clusters at the moment of their union. Inspecting a dendrogram provides deep intuitive insight into the natural hierarchical structure of your dataset. If two main branches merge at a very low height, it indicates that those subclusters are highly similar and closely packed. If a horizontal merge bar sits high up on the vertical axis, separated by a large vertical gap from the merges below it, it signals that the algorithm had to bridge a massive distance gap to join those distinct groups. This large vertical jump in merge height represents a natural boundary in the data hierarchy. However, static horizontal tree cutting across a single height threshold can fail when clusters possess varying internal densities or nested substructures at different depth levels. To solve this limitation, modern clustering frameworks employ dynamic tree cutting algorithms. Dynamic tree cutting evaluates the shape of dendrogram branches rather than relying on a static height cut. It analyzes branch length, subbranch gaps, and minimum cluster size constraints to iteratively split branches based on local density drops. A dense subcluster deep within the tree can be isolated cleanly, while broader, sparser clusters higher up are cut at a different effective height, enabling the discovery of complex, multi-density hierarchical partitions. To reorder dendrogram leaf nodes for visual presentation without altering the underlying tree topology, algorithms use optimal leaf ordering, or OLO. Optimal leaf ordering flips adjacent subtree branches at each node to minimize the distance between adjacent leaves in the linear plot, producing smooth, continuous visual transitions across clustered heat maps. Mathematically, a dendrogram imposes an ultrametric distance space on the dataset. In an ultrametric space, the cophonetic distance between any pair of points satisfies a strong triangle inequality. The cophonetic distance between points x and z is less than or equal to the maximum of the cophonetic distance between x and y and the cophonetic distance between y and z. To evaluate the mathematical fidelity of a dendrogram, researchers use the cophonetic correlation coefficient. When a dendrogram is constructed, the height at which any two specific data points are finally merged into a common cluster is called their cophonetic distance. If the dendrogram is an accurate representation of the original feature space, pairs of points that were close in the original distance matrix should have small cophonetic distances, and pairs that were far apart should have large cophonetic distances. The cophonetic correlation coefficient calculates the Pearson correlation coefficient between the original pairwise distances and the dendrogram cophonetic distances. A cophonetic correlation score close to 1 indicates that the hierarchical tree preserved pairwise relationships faithfully, whereas a low score warns that the chosen linkage criterion distorted the underlying geometry. Despite its rich interpretability and multiscale power, hierarchical clustering faces severe computational scaling bottlenecks. Naive implementations of agglomerative hierarchical clustering require big O of n-cubed time complexity. At each of the n-merge steps, a naive algorithm scans an n-by-n distance matrix to find the minimum distance pair. Using optimized priority queues and nearest neighbor chain algorithms, such as the SLINK algorithm for single linkage or the CLINK algorithm for complete linkage, the time complexity can be reduced to big O of n squared. High-performance C and C++ libraries like fastcluster utilize nearest neighbor chains to achieve big O of n-squared time complexity and linear space efficiency for specific linkage metrics. However, even big O of n-squared remains quadratic with respect to dataset size. If your dataset contains 100,000 observations, an n-squared matrix requires 10 billion distance entries, consuming tens of gigabytes of RAM just to store space matrix entries and executing trillions of calculations. Storing the full pairwise distance matrix requires big O of n-squared space. While standard k-means scales linearly in both memory and time, hierarchical clustering quickly exhausts hardware resources on large datasets. Consequently, in production system architectures, raw hierarchical clustering is rarely applied directly to raw datasets containing millions of rows. Instead, engineers employ hybrid architectures, first running mini-batch k-means or spatial binning to reduce millions of raw data points down to a few thousand representative centroids, and then applying Ward's agglomerative hierarchical clustering on those centroids to construct an interpretable macro-hierarchy. In conclusion, hierarchical clustering provides a deterministic, multi-scale framework for uncovering nested structure without prescribing cluster counts in advance. By selecting appropriate linkage criteria, whether single, complete, average, McQuitty, or Ward's, and analyzing dendrogram merge heights alongside cophonetic correlation, Lance-Williams recurrences, ultrametric trees, and dynamic tree cutting, software engineers can construct deep, domain-aligned taxonomies across complex datasets. Both centroid-based algorithms like k-means and variance-minimizing hierarchical algorithms like Ward's linkage operate under a rigid implicit geometric constraint. They assume clusters are convex, spherical blobs operating within a homogeneous density space. When data points form complex, non-spherical structures, such as concentric rings, winding spiral paths, connected linear networks, or irregularly shaped geographical regions, these classic algorithms fail completely. K-means will cut a crescent-shaped cluster into artificial spherical fragments, while Ward's linkage will force distinct dense regions to merge if they happen to sit near each other in space. Furthermore, real-world data is almost always contaminated with background noise, measurement errors, and extreme outliers. Forcing every noisy data point to belong to a cluster distorts cluster boundaries and degrades model accuracy. To overcome these fundamental limitations, system architects turn to density-based clustering, led by DBSCAN, Optics, dpclust, and HipScan. DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. Rather than assuming clusters have central centroids or spherical boundaries, DBSCAN defines a cluster as a contiguous region of high point density separated from other high density regions by areas of low point density. Imagine standing on a satellite view of Earth at night. Cities like Tokyo, London, or New York appear as dense, glowing clusters of light. Between these dense metropolitan centers stretch vast, dark regions of countryside and oceans containing sparse, isolated lights. DBSCAN views your feature space through this exact lens. Dense urban centers become valid clusters, while isolated rural lights are recognized as background noise. To operationalize density mathematically, DBSCAN relies on two fundamental hyperparameters: epsilon, often written as the Greek letter epsilon, and minimum points, abbreviated as min-PTS. Epsilon defines a spatial distance radius around any given data point. Imagine drawing an imaginary hypersphere of radius epsilon centered precisely at a specific data point. The epsilon neighborhood of that point consists of every other data point that falls within that distance radius. Minimum points specifies the threshold number of data points that must reside within a point's epsilon neighborhood for that region to be considered dense. Based on these two parameters, DBSCAN classifies every single data point in your dataset into one of three mutually exclusive categories: core points, border points, and noise points. A core point is any data point that contains at least minimum points within its epsilon neighborhood, including the point itself. Core points sit firmly inside the interior of a dense cluster region. They represent the high-density anchors of the dataset. A border point is a data point that is not a core point itself, meaning its own epsilon neighborhood contains fewer than minimum points, but it falls within the epsilon neighborhood of a core point. Border points sit along the outer perimeter of a cluster, bridging the boundary between high-density core regions and empty background space. A noise point is any data point that is neither a core point nor a border point. Its epsilon neighborhood contains fewer than minimum points, and it does not fall within the epsilon neighborhood of any core point. Noise points represent background clutter, measurement artifacts, or extreme outliers. Unlike k-means, which forcefully assigns every observation to a cluster, DBSCAN cleanly isolates noise points, assigning a label of -1 to indicate that they do not belong to any valid cluster. To form clusters from these point classifications, DBSCAN uses two formal relational definitions: direct density reachability and density connectivity. A point P is directly density reachable from a point Q if Q is a core point and point P falls within the epsilon neighborhood of Q. Notice that direct density reachability is asymmetric. If Q is a core point and P is a border point, P is directly density reachable from Q. However, because P is a border point and not a core point, Q is not directly density reachable from P. A point P is density reachable from a point Q if there exists a chain of intermediate points starting at Q and ending at P, where each consecutive point in the chain is directly density reachable from the point before it. If Q is a core point at the center of a city, and P is a border point at the edge of town, Q can reach P through a connected chain of overlapping core point neighborhoods. Finally, 2 points P and Q are density connected if there exists an intermediate point O such that both P and Q are density reachable from O. Density connectivity is symmetric. If 2 points sit on opposite sides of a sprawling, irregularly shaped cluster, they are density connected because a core point sitting in the middle of the cluster can reach both of them through overlapping epsilon neighborhoods. Using these rules, DBSCAN expands clusters through a systematic traversal algorithm. The algorithm begins by selecting an unvisited data point at random. It calculates the point's epsilon neighborhood. If the point contains fewer than minimum points, it is tentatively marked as noise. If the point contains at least minimum points, it is classified as a core point, and a new cluster is initiated. The algorithm then evaluates all points within its epsilon neighborhood. If any neighbor is also an unvisited core point, its own epsilon neighborhood is added to the active cluster expansion queue. The cluster grows organically, flooding outward along dense paths of overlapping epsilon neighborhoods like ink spreading across wet paper. The expansion halts only when the boundary of core points is reached and all density reachable border points have been attached. The algorithm then selects another unvisited point and repeats the process until every point in the dataset has been processed. One subtle operational edge case in DBSCAN is border point ambiguity. When two distinct clusters sit close to each other, a border point may fall within the epsilon neighborhood of core points belonging to both clusters. Because DBSCAN processes points sequentially, The border point will be assigned to whichever cluster expansion reaches it first. While this introduces minor non-deterministic behavior for border points, core point assignments remain perfectly deterministic regardless of processing order. This density propagation mechanism confers remarkable advantages. DBSCAN can discover clusters of arbitrary, complex geometries, including rings, interlocking horseshoes, and winding linear structures that completely baffle centroid-based algorithms. Furthermore, because DBSCAN isolates noise points automatically, its cluster boundaries remain untainted by distant outliers. However, standard DBSCAN faces significant operational challenges, most notably hyperparameter selection. Choosing optimal values for epsilon and minimum points requires careful domain analysis. A common diagnostic tool is the k-distance plot. To construct a k-distance plot, an engineer chooses a value for k, typically equal to minimum points, and calculates the distance from every point in the dataset to its kth nearest neighbor. These k-distances are sorted in ascending order and plotted on a continuous curve. The curve typically rises gently across dense regions and then bends sharply upward at an elbow point. This elbow point represents the boundary where local point density drops off dramatically. The k-distance value at the elbow serves as an optimal heuristic setting for epsilon. Despite this heuristic, standard DBSCAN suffers from a major structural limitation. It assumes a single, uniform global density across the entire feature space. If a dataset contains multiple valid clusters with vastly different internal densities, for example, one extremely dense cluster of financial transactions and another loosely scattered cluster of behavioral events, a single fixed epsilon parameter cannot capture both. If epsilon is set small to isolate the dense cluster, the sparser cluster will be classified entirely as background noise. Conversely, if epsilon is increased to capture the sparser cluster, the dense cluster will merge indiscriminately with neighboring regions. To address varying density without running full hierarchical frameworks, engineers sometimes use optics, which stands for ordering points to identify the clustering structure. Optics does not produce explicit clusters directly. Instead, it outputs an augmented ordering of the dataset that represents its density-based clustering structure. Optics defines two key concepts: core distance and reachability distance. The core distance of a point P is the smallest epsilon radius that would make P a core point. The reachability distance of a point P relative to a core point Q is the maximum of the core distance of Q and the Euclidean distance between P and Q. Optics processes points using a priority queue, ordering them such that points belonging to the same dense cluster are listed consecutively. When you visualize the reachability distances of points in this ordered sequence, dense clusters appear as deep valleys, while sparse regions and noise appear as high peaks separating the valleys. Slicing the reachability sequence at different height thresholds allows an engineer to extract clusters at multiple density scales simultaneously, bridging the gap between flat DBSCAN and hierarchical DBSCAN. Another alternative density paradigm is density peaks clustering, also known as dpclust or the decision graph method. Density peaks clustering assumes that cluster centers are surrounded by neighbors with lower local density and are at a relatively large distance from any points with higher local density. For each point, dpclust computes its local density ρ and its distance delta to the nearest point with higher density. By plotting delta against ρ on a decision graph, cluster centers emerge clearly as points with both high density ρ and large distance delta, allowing single-pass centroid discovery over complex density landscapes. To resolve the multi-density limitation of DBSCAN automatically, researchers developed DBSCAN, which stands for Hierarchical Density-Based Spatial Clustering of Applications with Noise. DBSCAN combines the non-spherical density expansion of DBSCAN with the multi-scale flexibility of hierarchical clustering. DBSCAN replaces the fixed epsilon distance parameter with a continuous density metric based on mutual reachability distance. First, DBSCAN calculates the core distance for every point, defined as the distance to its minimum points th nearest neighbor. A point sitting in a dense region has a small core distance, whereas a point in a sparse region has a large core distance. Next, the mutual reachability distance between any 2 points P and Q is defined as the maximum of 3 values: the core distance of P, the core distance of Q, and the actual spatial distance between P and Q. By defining distance through mutual reachability, DBSCAN effectively pushes sparse points further apart while keeping dense points close together. High-density points retain their natural spatial distance, but points in sparse regions are penalized by their large core distances, preventing noise bridges from forming between clusters. Using mutual reachability distance, DBSCAN constructs a minimum spanning tree over the dataset. It then transforms this minimum spanning tree into a hierarchy of connected components, producing a condensed cluster tree. Unlike standard hierarchical dendrograms that split down to individual singleton leaves, DBSCAN condenses the tree by ignoring tiny splits that contain fewer than minimum cluster size points. As you walk down the condensed tree, larger clusters lose individual points as noise or occasionally split into distinct, stable child clusters. Finally, DBSCAN extracts flat clusters from the condensed tree by measuring cluster stability. The stability of a cluster is calculated by integrating the density persistence of its constituent points over the range of mutual reachability distance thresholds for which the cluster exists in the tree. Clusters that persist over a wide range of density scales have high stability, whereas temporary clusters created by accidental density fluctuations disappear quickly. DBSCAN selects the set of non-overlapping clusters that maximizes total stability across the hierarchy. This allows DBSCAN to discover clusters of varying densities automatically, eliminating the need to tune a fixed epsilon hyperparameter. From a computational complexity perspective, naive implementations of DBSCAN require calculating pairwise distances between all points to find epsilon neighborhoods, yielding big O of n squared time complexity. However, by leveraging spatial indexing data structures, such as KD trees for low-dimensional spaces or R trees and ball trees for moderate dimensions, neighborhood queries can be computed in big O of n log n time. In high-dimensional spaces where spatial trees degrade due to the curse of dimensionality, approximate nearest neighbor search techniques like HNSW or ANOI are used to maintain subquadratic scalability. DBSCAN scales similarly, achieving big O of n log n complexity when spatial indexing is applicable. In production machine learning pipelines, density-based algorithms are the gold standard for spatial analysis, anomaly detection, telemetry clustering, and sensor network data processing. By defining clusters through local density and mutual reachability rather than geometric centroids, DBSCAN, optics, dpclust, and DBSCAN provide unmatched resilience against noise and non-spherical spatial geometries. In supervised machine learning, evaluating model performance is straightforward. You compare model predictions against ground truth labels using metrics like accuracy, precision, recall, or mean squared error. But in unsupervised clustering, ground truth labels do not exist. You are asking an algorithm to discover hidden structure within an unlabeled dataset, leaving you with a fundamental engineering dilemma. How do you evaluate whether the discovered clusters are meaningful, robust, and mathematically sound, or whether the algorithm simply partitioned random noise into arbitrary groups? Evaluating clustering performance requires rigorous statistical metrics. Clustering validation is divided into two major paradigms: internal evaluation metrics, which assess the quality of cluster boundaries using only the feature vectors and cluster assignments, and external evaluation metrics, which compare the algorithm's clusters against an external reference classification when ground truth labels are available for validation. We begin with internal evaluation metrics, which are essential for hyperparameter tuning, such as selecting the optimal number of clusters K, in real-world production environments where no ground truth exists. The most widely used internal metric is the silhouette coefficient. The silhouette coefficient measures how well each individual data point fits within its assigned cluster compared to neighboring clusters. To calculate the silhouette coefficient for a single data point I, we compute two values: the mean intracluster distance, denoted as A of I, and the mean nearest cluster distance, denoted as B of I. The mean intracluster distance, A of I, is the average Euclidean distance between data point I and all other data points belonging to the same cluster. A small value for A of I indicates that point I is located deep inside a dense, compact cluster. The mean nearest cluster distance, B of I, is calculated by measuring the average distance from data point I to all data points in each neighboring cluster, and selecting the minimum average distance among all other clusters. The neighboring cluster that yields this minimum average distance is considered the nearest neighbor cluster to point I. The silhouette coefficient for point I is defined as B of I minus A of I, divided by the maximum of A of I and B of I. This formulation produces a normalized score ranging strictly between -1 and +1. Understanding the interpretation of this range provides deep diagnostic power. A silhouette score close to +1 means that A of I is much smaller than B of I, indicating that the data point is tightly bound within its own cluster and far away from neighboring clusters. This represents ideal cluster separation. A silhouette score near 0 means that A of I is approximately equal to B of I, indicating that the data point sits right on the decision boundary between two adjacent clusters. A negative silhouette score means that A of I is larger than B of I, signaling a severe misclassification. The point is actually closer on average to a neighboring cluster than to the cluster it was assigned to. By averaging the silhouette coefficients across all individual data points in the dataset, we obtain the mean silhouette coefficient for the entire clustering configuration. When tuning K and K-means, engineers run the algorithm across a range of K values, say, from K equals 2 to K equals 20, and plot the mean silhouette coefficient against K. The K value that yields the highest peak on the silhouette curve represents the optimal balance of compactness and separation. Beyond the mean silhouette coefficient, engineers analyze silhouette plots, which visualize the individual silhouette scores of points within each cluster sorted by magnitude. A healthy clustering configuration exhibits silhouette profiles where all clusters have roughly equal width and high average scores. If one cluster displays a wide, deep tail of negative silhouette scores, it reveals that the algorithm forced an unnatural grouping or split a true cluster in half. A second major internal evaluation metric is the Davies-Bouldin index. Unlike the silhouette coefficient, which evaluates individual points, the Davies-Bouldin index evaluates the overall similarity between clusters based on their dispersion and distance. To compute the Davies-Bouldin index, we first define the internal dispersion of a cluster, denoted as S of I, calculated as the average distance between all points in cluster I and their cluster centroid. Next, we measure the distance between cluster centroids, d of Ci and Cj, defined as the spatial distance between the centroid of cluster I and the centroid of cluster J. The similarity R of Ij between cluster I and cluster J is defined as the sum of their internal dispersions, S of I plus S of J, divided by the distance between their centroids, d of Ci and Cj. Notice what this ratio captures. If two clusters are spread out and sit close to each other, S of I plus S of J is large while d of Ci and Cj is small, resulting in a high similarity ratio. If two clusters are dense and far apart, S of I plus S of J is small while d of Ci and Cj is large, resulting in a low similarity ratio. For each cluster I, the algorithm finds the maximum similarity ratio R of Ij across all other clusters J. The Davies-Bouldin index is then calculated as the average of these maximum similarity ratios across all K clusters. Because lower similarity ratios reflect denser, more isolated clusters, a lower Davies-Bouldin index indicates a superior clustering configuration. A Davies-Bouldin index approaching 0 represents ideal separation. A third key internal evaluation metric is the Kolinsky-Hierarchical index, also known as the variance ratio criterion. The Kolinsky-Hierarchical index measures the ratio of total between cluster variance to total within cluster variance, scaled by their respective degrees of freedom. The between cluster variance measures how far the individual cluster centroids sit from the global mean centroid of the entire dataset, weighted by the number of points in each cluster. High between cluster variance means centroids are well separated across space. The within cluster variance measures the total sum of squared distances between points and their respective cluster centroids. Low within cluster variance means data points are tightly clustered around their centroids. The Kolinsky-Hierarchical index multiplies the ratio of between cluster variance to within cluster variance by n-k divided by k-1, where n is the total number of data points and k is the number of clusters. Because high between cluster dispersion and low within cluster dispersion produce a large ratio, higher Kolinsky-Hierarchical scores indicate better defined, more distinct clusters. The Kolinsky-Hierarchical index is computationally lightweight to compute compared to the silhouette coefficient, making it ideal for evaluating large-scale datasets. Other specialized internal validation metrics include the Dunn index, the separation index, and the COP index. The Dunn index calculates the ratio of the minimum intercluster distance between any 2 points in different clusters to the maximum cluster diameter across the dataset. Higher Dunn index values indicate compact, well-separated clusters, though the metric is sensitive to noise. The COP index evaluates the ratio of intracluster distance to intercluster distance, penalizing clusters with high internal variance. Now let us turn to external evaluation metrics. External metrics are used when ground truth class labels are available for a validation subset, or when evaluating how closely an unsupervised clustering model aligns with a known domain classification. The most fundamental external metric is the Adjusted Rand Index, or ARI. The Rand Index evaluates cluster quality by examining all possible pairs of data points in the dataset. For a dataset of n points, there are n times n-1 divided by 2 distinct pairs. The algorithm classifies each pair into one of 4 categories: pairs that belong to the same group in both ground truth and predicted clusters, pairs that belong to different groups in both, pairs that belong to the same group in ground truth but different predicted clusters, and pairs that belong to different ground truth groups but the same predicted cluster. The row-rand index is the proportion of concordant pairs, those agreed upon by both ground truth and predicted clusters, divided by the total number of pairs. However, the row-rand index suffers from a major flaw. Its expected value for two random clusterings is not zero. As the number of clusters increases, chance agreement inflates the row-rand index. The adjusted rand index solves this by correcting for chance. It computes the row-rand index, subtracts the expected rand index under a random permutation model, and divides by the maximum possible rand index minus the expected rand index. The adjusted rand index yields a normalized score where a value of 1 indicates perfect agreement between predicted clusters and ground truth. A score of 0 represents agreement no better than random guessing, and negative scores indicate worse than random agreement. Another important external metric is normalized mutual information, or NMI. Normalized mutual information measures the amount of shared information between predicted cluster assignments and ground truth class labels using information theory. It calculates the mutual information between the two label distributions and normalizes it by the arithmetic or geometric mean of their individual Shannon entropies. NMI ranges from 0, indicating completely independent labelings with 0 shared information, to 1, indicating perfect mutual information alignment. To complement NMI, researchers use homogeneity, completeness, and V-measure. Homogeneity measures whether each cluster contains only data points that are members of a single class. A clustering result satisfies homogeneity if every cluster is pure. Completeness measures whether all data points that are members of a given class are assigned to the same cluster. V-measure is the harmonic mean of homogeneity and completeness, providing a single balanced metric analogous to the F1 score in supervised classification. Additional metrics like the Folks-Mallows index compute the geometric mean of pairwise precision and recall, while variation of information measures entropy gain. Beyond static internal and external metrics, production machine learning systems rely on cluster stability analysis. Cluster stability evaluates how consistently an algorithm reproduces similar cluster structures when trained on different random subsamples or perturbed versions of the same dataset. In stability analysis, engineers apply bootstrapping, repeatedly drawing random subsamples of 70 to 80% of the data, running the clustering algorithm on each subsample, and measuring the pairwise similarity between the resulting clusterings using the adjusted rand index. If an algorithm consistently discovers identical cluster boundaries across different random subsamples, the cluster structure is highly stable and represents genuine underlying phenomena. If minor sampling perturbations produce completely different cluster assignments, the clusters are unstable artifacts of sampling noise. In conclusion, robust clustering evaluation requires combining multiple metrics. Relying on a single metric can be misleading. K-means will almost always maximize the Kolinsky-Harabass index because both optimize squared Euclidean distances, while DBSCAN may yield lower silhouette scores due to noise point isolation. By synthesizing silhouette analysis, Davies-Bolden scores, Kolinsky-Harabass variance ratios, Dunn indices, external metrics like ARI and NMI, and bootstrapping stability tests, software engineers build rigorous, empirically verified unsupervised learning systems. When building machine learning systems in high-dimensional feature spaces, such as processing high-resolution images with millions of pixels, genomic sequences with tens of thousands of genes, or text documents represented as massive sparse vocabulary vectors, engineers immediately run into severe operational bottlenecks. High-dimensional data demands enormous storage capacity and compute infrastructure, inflates latency during real-time inference, and triggers the curse of dimensionality, where distance metrics lose diagnostic contrast. Furthermore, high-dimensional datasets are frequently plagued by multicollinearity, where dozens of features measure essentially the same underlying phenomenon under different names. To condense complex feature spaces while preserving essential information, we turn to dimensionality reduction and its premier foundational technique, Principal Component Analysis, or PCA. Principal Component Analysis is an unsupervised linear transformation technique designed to compress high-dimensional feature spaces into a smaller set of uncorrelated continuous variables called principal components. To build an intuitive mental model of PCA, imagine holding a complex three-dimensional wire sculpture in your hands under a bright overhead lamp. As you rotate the sculpture in the light, it casts a two-dimensional shadow onto the floor below. If you hold the sculpture at an arbitrary angle, the shadow might compress into a meaningless, overlapping blob of lines. However, if you carefully align the sculpture so that its longest, widest dimensions stretch parallel to the floor, the shadow captures the rich, intricate structural silhouette of the original object with minimal distortion. PCA is the mathematical process of finding the absolute best angles from which to view high-dimensional data so that its projected lower-dimensional shadow retains the maximum possible structural detail. From a geometric perspective, PCA achieves compression by projecting data points onto a lower-dimensional linear subspace, such as a line, plane, or hyperplane. The goal of PCA can be defined through two equivalent mathematical perspectives: maximizing the variance of the projected data points, or minimizing the total squared reconstruction error between the original high-dimensional points and their low-dimensional projections. Consider projecting a cloud of data points onto a single straight line. If you choose a line that runs perpendicular to the main direction of variation in the data cloud, all the projected points collapse into a tight, overlapping pile, squashing the natural variance of the dataset down to near zero. You have destroyed information. Conversely, if you choose a line that aligns perfectly with the longest axis of elongation in the data cloud, the projected points spread out as far as possible along the line, retaining maximum variance. The direction in feature space along which the data exhibits the absolute highest variance is defined as the first principal component. Once the first principal component direction is established, the second principal component is defined as the direction that maximizes remaining variance subject to a strict geometric constraint. It must be perfectly orthogonal or perpendicular to the first principal component. This orthogonality constraint guarantees that the second principal component captures entirely new, non-redundant information, exhibiting zero linear correlation with the first component. Each subsequent principal component follows this exact rule. It maximizes remaining variance while remaining orthogonal to all previously defined principal components. To understand the mathematical mechanics of PCA, let us walk through its derivation step by step using natural matrix algebra concepts. The process begins with a data matrix X, consisting of n rows representing individual observations and d columns representing feature variables. The absolute mandatory first step in PCA is mean centering the data matrix. We calculate the mean value of each feature column across all n rows and subtract that column mean from every entry in the feature column. Mean centering shifts the origin of the coordinate system directly to the geometric center of mass of the data cloud. If feature variables operate on different units or scales, such as weight in kilograms versus age in years, we must also standardize each column by dividing by its standard deviation, ensuring that every feature has a mean of 0 and a variance of 1. Failing to standardize unscaled data causes PCA to falsely identify the raw feature with the largest numerical scale as the dominant principal component. Once the data matrix X is standardized, we compute the sample covariance matrix, denoted as S. The sample covariance matrix S is a symmetric D by D matrix calculated as 1 divided by n minus 1 times X transpose times X. Each off-diagonal entry in S represents the sample covariance between two feature variables, capturing how they covary together. The diagonal entries represent the variance of each individual feature variable. Now, imagine choosing a unit direction vector W in feature space onto which we will project our standardized data points. The variance of the projected data points along direction W can be expressed algebraically as W transpose times the sample covariance matrix S times W. Our mathematical objective is to find the direction vector W that maximizes this projected variance, subject to the constraint that W is a unit vector, meaning W transpose times W equals 1. To solve this constrained optimization problem, we formulate the Lagrangian function, defined as W transpose times S times W minus a Lagrange multiplier scalar lambda times the quantity W transpose times W minus 1. To find the maximum, we take the partial derivative of the Lagrangian function with respect to the vector W and set it equal to 0. This optimization derivative yields the fundamental characteristic equation of PCA. The sample covariance matrix S times the direction vector W equals lambda times W. This equation is the precise mathematical definition of an eigenvector problem. The vector W is an eigenvector of the covariance matrix S, and the scalar lambda is its corresponding eigenvalue. This mathematical result reveals a profound truth. The principal component directions of a dataset are precisely the eigenvectors of its sample covariance matrix, and the variance captured along each principal component direction is equal to its corresponding eigenvalue. Because the sample covariance matrix S is a symmetric matrix, its eigenvectors are mathematically guaranteed to be orthogonal to one another, satisfying our geometric requirement. Sorting the eigenvalues in descending order from largest to smallest establishes the ranking of principal components. The eigenvector associated with the largest eigenvalue represents the first principal component, capturing the maximum variance in the data. The eigenvector associated with the second largest eigenvalue represents the second principal component, and so on. In modern high-performance numerical computing libraries, PCA is rarely implemented by explicitly constructing the sample covariance matrix and computing its eigenvalue decomposition. Constructing the covariance matrix X transpose times X can introduce numerical instability and precision loss due to floating point rounding errors when features have collinear relationships. Instead, production PCA implementations compute principal components directly on the standardized data matrix X using singular value decomposition, or SVD. Singular value decomposition factorizes any real-valued n by d data matrix X into the product of three matrices: an n by n orthogonal matrix U containing the left singular vectors, an n by d rectangular diagonal matrix sigma containing singular values, and a d by d orthogonal matrix V transpose containing right singular vectors. The mathematical relationship between SVD and eigenvalue decomposition is elegant and direct. The right singular vectors in V are identical to the eigenvectors of the covariance matrix X transpose times X. Furthermore, the singular values on the diagonal of matrix sigma are directly proportional to the square roots of the eigenvalues. Each eigenvalue lambda of the covariance matrix equals the square of its corresponding singular value sigma, divided by n minus 1. Computing PCA via SVD avoids explicit matrix multiplication, offering superior numerical precision, memory efficiency, and computational stability. For massive streaming matrices where computing full SVD is prohibitive, systems use randomized PCA, such as the Hawko-Martenson-Trop algorithm. Randomized PCA uses random projection matrices to find a low-rank approximation of matrix X in sublinear time, enabling instant principal component extraction on massive datasets. When probabilistic interpretations are required, engineers use probabilistic PCA, or PPCA. Probabilistic PCA formulates PCA as a latent variable model under a Gaussian likelihood distribution, optimizing parameters via expectation maximization to handle missing feature values naturally. Once the principal component eigenvectors and eigenvalues are computed, an engineer must decide how many principal components to retain for downstream tasks. To make an informed choice, we analyze the explained variance ratio. The explained variance ratio of a specific principal component is calculated by dividing its individual eigenvalue by the sum of all eigenvalues across the entire dataset. This ratio expresses the percentage of total dataset variance captured by that specific component. By computing the cumulative explained variance, the running sum of explained variance ratios across the top k components, engineers evaluate the trade-off between dimensionality reduction and information loss. A common diagnostic tool is the scree plot, which plots the individual eigenvalues or explained variance percentages on the vertical axis against the component index on the horizontal axis. In a typical scree plot, the variance drops steeply across the first few components and then levels off into a flat horizontal line, resembling an elbow joint. The elbow point on the scree plot indicates the threshold beyond which additional principal components capture mostly background noise rather than structural signal. In production pipelines, engineers typically select the minimum number of components required to preserve a target cumulative variance threshold, such as 90 or 95% of total dataset variance. To project the original n by d dataset X into a reduced k-dimensional space, we construct a d by k projection matrix P containing the top k eigenvector columns. Multiplying the standardized data matrix X by the projection matrix P produces an n by k transformed dataset, representing the original data projected onto the k principal component axis. While standard linear PCA is remarkably powerful, system architects must navigate several advanced variants tailored to specific operational constraints. For massive out-of-core datasets that exceed system RAM, incremental PCA provides an online streaming approach. Incremental PCA processes data in small mini-batches, updating the singular value decomposition incrementally using randomized linear algebra updates. This enables dimensionality reduction over terabyte-scale datasets using modest memory footprints. For datasets with sparse feature matrices, such as term document frequency matrices in natural language processing, standard PCA destroys sparsity because mean centering subtracts non-zero column means from millions of zero entries, turning a memory-efficient sparse matrix into a massive dense matrix. Sparse PCA resolves this by adding an L1 regularization penalty to the principal component optimization objective, forcing the resulting weight vectors to contain true zero coefficients while preserving feature matrix sparsity. For noisy datasets containing sparse gross corruption errors, engineers use robust PCA, or RPCA. Robust PCA decomposes data matrix X into the sum of a low-rank matrix L capturing true structural variance, and a sparse matrix S capturing corrupt outliers, using principal component pursuit optimization. Finally, when data points lie on complex nonlinear curved surfaces, such as a Swiss roll manifold, linear PCA fails because a flat hyperplane cannot unroll curved geometry without tearing or compressing distant points together. Kernel PCA overcomes this limitation by combining PCA with the kernel trick. Kernel PCA maps the original data into a high-dimensional implicit feature space using a nonlinear kernel function, such as a radial basis function or polynomial kernel, and performs linear PCA within that transformed space. This allows kernel PCA to discover complex, nonlinear subspace structures, bridging linear algebra with nonlinear manifold learning. In conclusion, principal component analysis is an indispensable, while linear dimensionality reduction techniques like principal component analysis excel at finding flat orthogonal hyperplanes of maximal variance. Real-world high-dimensional data frequently resides on complex, nonlinear manifolds. Imagine taking a flat two-dimensional sheet of paper, painting a complex multicolored pattern on it, rolling it up tightly like a cylinder or a Swiss roll, and dropping it into a three-dimensional room. In the three-dimensional room, 2 points that were far apart on opposite edges of the flat paper may now sit physically right next to each other in space due to the curvature of the roll. If you apply linear PCA to project this Swiss roll onto a flat two-dimensional plane, it will squish the layers together, blending completely different parts of the pattern and destroying the natural manifold geometry. To visualize complex, nonlinear high-dimensional structures on a two-dimensional screen or dashboard, engineers rely on nonlinear manifold learning techniques. Among these, two algorithms dominate modern data science and software engineering: t-distributed stochastic neighbor embedding, known as t-SNE, and uniform manifold approximation and projection, known as UMAP. We begin with t-distributed stochastic neighbor embedding, or t-SNE, developed specifically to map high-dimensional feature spaces into 2 or 3 dimensions for human visual inspection. t-SNE converts spatial distances between data points into conditional probabilities that represent pairwise similarities. In the original high-dimensional space, t-SNE models local neighborhoods using a Gaussian probability distribution. For any pair of data points I and j, t-SNE calculates the conditional probability p of j given I, defined as the probability that point I would pick point j as its neighbor if neighbors were sampled under a Gaussian distribution centered at point I. The variance of this Gaussian distribution, sigma sub I, is not fixed globally across the dataset. Rather, it is adapted dynamically for each individual data point based on local density. To control this adaptive variance, t-SNE introduces its most critical hyperparameter, perplexity. Perplexity can be interpreted as a smooth measure of the effective number of nearest neighbors each data point considers when forming its local neighborhood. Typical perplexity values range between 5 and 50. In dense regions of feature space, the algorithm automatically shrinks the Gaussian variance sigma sub I to maintain the target perplexity, whereas in sparse regions it expands sigma sub I. To make distance calculations symmetric and robust to outliers, t-SNE converts these conditional probabilities into joint probabilities, p sub ij, by averaging p of j given I and p of I given j across all data points and dividing by the total dataset size n. This ensures that every pair of points shares a symmetric high-dimensional similarity score. Next, t-SNE initializes a low-dimensional map, placing every data point at a random location in a two-dimensional space. In this low-dimensional space, t-SNE measures the similarity between low-dimensional points I and j, denoted as q sub ij. However, t-SNE does not use a Gaussian distribution for low-dimensional similarities. Instead, it uses a heavy-tailed student t-distribution with 1 degree of freedom, which is mathematically identical to a Cauchy distribution. The choice of a student t-distribution in the low-dimensional space is a stroke of algorithmic genius designed to solve a fundamental geometric pathology known as the crowding problem. To visualize the crowding problem, imagine 10 points in a 10-dimensional space that are all mutually equidistant from one another, like the vertices of a regular 10-dimensional hypersimplex. In 10 dimensions, there is ample space for all 10 points to sit equal distances apart. However, when you attempt to map those 10 mutually equidistant points into a flat 2-dimensional space, it is physically impossible for all 10 points to remain equidistant. In lower dimensions, the volume of a sphere of radius are scales as are squared, whereas in a d-dimensional space, volume scales as are to the power of d. High-dimensional spaces have vastly more volume at large distances than low-dimensional spaces. Consequently, when projecting high-dimensional data into 2 dimensions, moderate distances in high dimensions collapse into tiny, crowded distances in low dimensions, causing distinct subclusters to squash together into an uninterpretable central blob. By using a heavy-tailed student t-distribution in the low-dimensional map, Q sub ij falls off much more slowly at moderate spatial distances than the high-dimensional Gaussian distribution P sub ij. To achieve a low-dimensional similarity score Q sub ij that matches a given high-dimensional similarity score P sub ij, the low-dimensional points must be placed much further apart. The heavy tails of the student t-distribution effectively blow open the crowded low-dimensional space, allowing clusters to separate cleanly with wide empty spaces between them. The mathematical goal of t-SNE is to minimize the discrepancy between the high-dimensional probability distribution P and the low-dimensional probability distribution Q across all pairs of points. t-SNE measures this discrepancy using Kullback-Leibler divergence, or KL divergence. The objective function is the sum of P sub ij times the logarithm of P sub ij divided by Q sub ij across all pairs. t-SNE minimizes KL divergence using gradient descent. The gradient acts like a system of physical forces acting on the low-dimensional points. Spring-like attractive forces pull points together if their high-dimensional similarity P sub ij is large, while repulsive forces push points apart if their low-dimensional similarity Q sub ij is larger than it should be. Despite its exceptional visual clarity, standard t-SNE suffers from major operational drawbacks. First, t-SNE does not preserve global structure. Because KL divergence penalizes assigning small low-dimensional probabilities Q sub ij to large high-dimensional probabilities P sub ij heavily, but imposes near-zero penalty when small high-dimensional probabilities are mapped to low-dimensional points, t-SNE prioritizes local neighbor preservation at the complete expense of global distances. The relative distance between 2 distant clusters on a t-SNE plot is largely arbitrary and meaningless. You cannot infer that cluster A is closer in original feature space to cluster B than to cluster C simply because they appear closer on a t-SNE map. Second, t-SNE is computationally expensive. Naive t-SNE requires big O of n squared time complexity per iteration. Modern implementations use spatial tree approximations, such as Barnes-Hut t-SNE, which reduces complexity to big O of n log n by grouping distant points into quadtrees or octrees. Fast Fourier transform accelerated t-SNE, known as FIT-SNE, further accelerates computation to linear big O of n scaling by interpolating electrical field forces on equispace grids, enabling visualization of millions of data points. Third, t-SNE is non-parametric and non-deterministic. It does not learn a reusable projection function. You cannot fit a t-SNE model on training data and subsequently project new, unseen out-of-sample data points onto the existing map. Furthermore, because t-SNE starts from random initialization, running the algorithm twice on the exact same dataset produces visually different cluster layouts unless the random seed is fixed. To overcome these limitations while maintaining exceptional nonlinear visualization performance, researchers developed UMAP, which stands for Uniform Manifold Approximation and Projection. UMAP is built upon solid theoretical foundations in Riemannian geometry and algebraic topology. UMAP assumes that data points reside on a continuous Riemannian manifold embedded within a higher dimensional ambient space, and that the local metric on this manifold is locally constant. To construct its high-dimensional representation, UMAP constructs a weighted k-nearest neighbor graph, representing the dataset as a fuzzy simplicial set using Čech and Vietoris-Rips complexes. In this graph, edge weights between points reflect fuzzy membership probabilities, representing the likelihood that a continuous edge exists between 2 points on the manifold. UMAP uses an adaptive local metric for each point, scaling local distances by the distance to its immediate nearest neighbor. This local scaling ensures that UMAP adapts automatically to varying point densities across different regions of the manifold. To project this fuzzy graph into a lower dimensional space, UMAP constructs a corresponding low-dimensional fuzzy simplicial set graph. Instead of using KL divergence, UMAP minimizes the fuzzy set cross-entropy between the high-dimensional graph fuzzy weights and the low-dimensional graph fuzzy weights. Fuzzy set cross-entropy contains two distinct terms: a term that acts like attractive forces pulling neighbor points together, and a secondary term that acts like repulsive forces pushing non-neighbor points apart across the entire manifold. This dual optimization in UMAP produces a critical architectural advantage. UMAP preserves both local neighborhood structure and global manifold topology. Clusters that are far apart in the original high-dimensional feature space remain far apart on the UMAP projection, allowing engineers to interpret both local cluster membership and macro-scale global relationships reliably. Furthermore, UMAP exposes two intuitive operational hyperparameters: n_neighbors and min_dist. The n_neighbors parameter controls the size of the local neighborhood evaluated when constructing the fuzzy graph, similar to perplexity in t-SNE. Low values of n_neighbors force UMAP to concentrate on fine-grained local structure, isolating small subclusters. High values of n_neighbors force UMAP to encompass broader global contexts, preserving macro-scale manifold topology. The min_dist parameter controls the minimum distance between points in the low-dimensional projection. Low min_dist values force data points to pack tightly together into dense visual clusters, highlighting discrete boundaries. High min_dist values allow points to spread out smoothly, preserving continuous manifold variations. From a performance standpoint, UMAP utilizes nearest neighbor descent to construct its k-nearest neighbor graph efficiently, achieving big O of n scaling. It executes significantly faster than Barnes-Hut t-SNE on large datasets. Furthermore, parametric UMAP trains a deep neural network to learn the UMAP embedding function directly, allowing software engineers to freeze a trained UMAP model and project incoming streaming out-of-sample data points into the low-dimensional space in production inference pipelines. In comparative summary, linear PCA provides fast, deterministic, variance-maximizing projections that preserve global Euclidean distances but fail on curved manifolds. t-SNE delivers stunning, highly separated cluster visualizations by solving the crowding problem through student t-distributions, but distorts global distances and cannot transform unseen out-of-sample data natively. UMAP combines the best of both worlds, using fuzzy simplicial sets to preserve both local clusters and global topology with subquadratic computational speed and full support for parametric out-of-sample inference. While linear methods like PCA find flat projections and manifold algorithms like t-SNE or UMAP construct graph embeddings for static visualization, modern deep learning offers a unified, highly scalable neural framework for nonlinear dimensionality reduction. Autoencoders. An autoencoder is a specialized neural network architecture designed to learn compressed, low-dimensional representations of input data in an unsupervised manner. Unlike traditional neural networks that are trained to map input features to external target labels, an autoencoder is trained to perform self-supervised reconstruction. It takes an input vector x, passes it through a series of structural transformations, and attempts to reconstruct the exact original input vector x as its output. To prevent the neural network from simply learning a trivial identity function, where it blindly passes input values directly to output nodes without learning anything meaningful, the autoencoder introduces a structural constraint known as the bottleneck layer. An autoencoder architecture consists of three core components: the encoder, the latent space bottleneck, and the decoder. The encoder is a neural network pipeline that takes an input feature vector x of dimension d and passes it through one or more hidden layers, progressively compressing its spatial dimension down to a low-dimensional bottleneck layer of dimension k, where k is significantly smaller than d. The vector produced at this bottleneck layer is called the latent code, latent representation, or embedding vector z. The latent space represents the compressed feature manifold. Every input vector is mapped to a single point in this k-dimensional continuous latent space, capturing the essential nonlinear factors of variation present in the raw data. The decoder is a symmetric neural network pipeline that takes the latent code z from the bottleneck layer and passes it through expanding hidden layers, attempting to reconstruct a high-dimensional output vector x hat that matches the original input vector x as closely as possible. To train an autoencoder, we define a reconstruction loss function that measures the discrepancy between the original input vector x and the reconstructed output vector x hat. If the feature variables are continuous unbounded values, we use mean squared error as the reconstruction loss, calculating the average squared Euclidean distance between corresponding elements of x and x hat. If the feature variables are normalized continuous values between 0 and 1, such as image pixel intensities, we use binary cross-entropy loss, treating each normalized output node as a Bernoulli probability distribution. The parameters of both encoder and decoder networks are optimized simultaneously using gradient descent and backpropagation to minimize this reconstruction loss across the training dataset. To understand the mathematical relationship between autoencoders and classical dimensionality reduction, consider a linear autoencoder. A linear autoencoder is an autoencoder that uses purely linear activation functions across all hidden layers and is trained using mean squared error loss. If you train a linear autoencoder with a k-dimensional bottleneck layer on a standardized dataset, a remarkable mathematical equivalence emerges. The k-dimensional subspace spanned by the bottleneck latent vectors is mathematically identical to the k-dimensional principal subspace discovered by principal component analysis. The encoder weight matrix aligns with the top k principal component eigenvectors of the covariance matrix. While the individual weight vectors learned by a linear autoencoder may be rotated versions of the principal eigenvectors, the reconstructed outputs and the total variance captured within the latent space are identical to PCA. However, the true power of autoencoders lies in their ability to transcend linear projections. By introducing nonlinear activation functions, such as rectified linear units, leaky ReLU, GELU, or Swish, into the hidden layers of deep neural network architectures, autoencoders learn highly complex, nonlinear manifolds. A deep nonlinear autoencoder can fold, unroll, and warp complex high-dimensional geometric surfaces. For example, when processing high-resolution images using convolutional autoencoders, early encoder layers learn simple localized edge detectors, middle layers combine edges into geometric textures and shapes, and deep bottleneck layers compress entire complex semantic objects into compact continuous latent vectors. When processing sequence telemetry, recurrent and transformer autoencoders compress temporal dynamics into fixed latent representations. Beyond standard deterministic autoencoders, modern machine learning systems rely on regularized autoencoder variants designed to enforce specific structural properties within the latent space. Three prominent regularized architectures are denoising autoencoders, sparse autoencoders, and contractive autoencoders. A denoising autoencoder is designed to prevent the network from memorizing input data and to force it to learn robust manifold features. During training, a denoising autoencoder deliberately corrupts the clean input vector x by adding zero-mean Gaussian noise or randomly zeroing out a fraction of input features using dropout, producing a noisy input vector x tilde. The corrupted vector x tilde is passed into the encoder to produce latent code z, but the decoder is forced to minimize reconstruction loss against the original clean input vector x. To succeed at reconstructing the clean input from a corrupted version, the network cannot simply learn local memorization. It must learn the underlying statistical dependencies and structural constraints that govern valid data points on the data manifold. Imagine listening to a favorite song over a static-filled radio line. Your brain easily fills in missing notes because you understand the underlying structure of music. A denoising autoencoder acts like that intelligent brain, projecting noisy off-manifold points back onto the dense core of the valid data manifold. A sparse autoencoder enforces sparsity constraints on the latent representation, forcing only a tiny fraction of latent bottleneck neurons to be active or non-zero for any given input point. Sparse representations are biologically inspired by the human visual cortex, where billions of neurons exist but only a small subpopulation fires in response to a specific visual stimulus. To enforce sparsity mathematically, a sparse autoencoder adds a regularization penalty term to the reconstruction loss function. One common approach is adding an L1 norm penalty on the bottleneck activations. Another approach measures the Kullback-Leibler divergence between the average activation of each bottleneck neuron across a training batch and a target low sparsity parameter, such as 0.05. If a neuron fires too frequently, the KL penalty surges, forcing the encoder weights to adjust. Sparse autoencoders discover highly specialized, interpretable feature detectors that act like dictionary basis vectors for complex input spaces. A contractive autoencoder enforces spatial smoothness on the encoder mapping by adding a penalty term that measures how sensitive the latent code Z is to small perturbations in the input vector X. This penalty is calculated as the Frobenius norm of the Jacobian matrix of the encoder activations with respect to the input features. The Jacobian matrix stores all first-order partial derivatives of the latent code outputs with respect to the input variables. A small Jacobian-Frobenius norm means that moving slightly away from an input point in feature space causes almost zero change in the latent code Z. The contractive penalty forces the encoder to flatten out minor input noise along directions orthogonal to the data manifold, ensuring that latent representations remain invariant to irrelevant input fluctuations while preserving significant structural variations along the manifold surface. Despite the power of regularized autoencoders, standard deterministic autoencoders suffer from an important generative limitation. Their latent space often contains vast empty regions and discontinuous gaps. If you sample a random latent vector Z from an unconstrained empty region of the latent space and feed it into the decoder, the network will generate a corrupted, meaningless output. The latent space lacks smooth, probabilistic continuity. To build a continuous, smooth probabilistic latent space suitable for both dimensionality reduction and generative sampling, researchers developed the variational autoencoder, or VAE. A variational autoencoder replaces deterministic latent vectors with a probabilistic latent distribution. Instead of mapping an input vector X directly to a single fixed latent code vector Z, the VAE encoder outputs two continuous parameters for each latent dimension: a mean vector, mu, and a log variance vector, log of sigma squared. These two vectors define a multivariate Gaussian probability distribution in latent space. To generate a latent code Z during forward propagation, the VAE samples a random vector from this Gaussian distribution using the mean mu and variance sigma. However, sampling a random vector from a probability distribution introduces a critical mathematical roadblock. Sampling is a stochastic, non-differentiable operation. You cannot calculate partial derivatives through a random sampling step, which completely breaks standard backpropagation and gradient descent. To solve this non-differentiable roadblock, variational autoencoders use a clever mathematical trick known as the reparameterization trick. Instead of sampling the latent code vector Z directly from the learned Gaussian distribution with mean mu and standard deviation sigma, the reparameterization trick decouples the stochastic randomness from the network parameters. The algorithm samples an independent noise vector epsilon from a standard normal Gaussian distribution with zero mean and unit variance. This standard normal vector epsilon requires zero trainable parameters. The latent code vector Z is then calculated deterministically as mu plus sigma element-wise multiplied by epsilon. By shifting the stochastic randomness out into the independent vector epsilon, the latent code Z becomes a deterministic, differentiable function of the encoder outputs mu and sigma. Gradients flow smoothly backwards through mu and sigma during backpropagation, enabling end-to-end neural network optimization. The loss function of a variational autoencoder consists of two distinct mathematical components: the reconstruction loss and the evidence lower bound Kullback-Leibler (KL) divergence regularization loss. The reconstruction loss measures how accurately the decoder reconstructs the input vector X from the sampled latent code Z, using mean squared error or binary cross-entropy. The KL divergence loss measures how much the learned latent probability distribution, defined by mean mu and variance sigma, deviates from a standard multivariate Gaussian prior distribution with zero mean and unit variance. These two loss components create an elegant architectural tension. The reconstruction loss pushes the encoder to spread out latent distributions for different input classes into distinct, separated regions of latent space so the decoder can reconstruct them accurately. Conversely, the KL divergence loss pulls all latent distributions toward the center of space, forcing them to overlap and align with the standard normal Gaussian distribution. To enforce disentanglement, where individual latent dimensions correspond to isolated, independent physical attributes, engineers use beta VAES, which scale the KL divergence loss penalty by a coefficient beta. Higher beta values force latent dimensions to decouple cleanly. For discrete latent spaces, vector quantized VAEs, or VQVAES, use codebook quantization to learn discrete latent structures. In software system architecture, autoencoders provide unmatched versatility. They serve as multimodal feature extractors for downstream classifiers, real-time anomaly detection engines by flagging inputs with abnormally high reconstruction error, and nonlinear compression modules in production data pipelines. By combining deep nonlinear neural networks with regularization and probabilistic latent spaces, autoencoders bridge unsupervised dimensionality reduction with modern generative AI modeling. Understanding theoretical formulations and mathematical derivations is essential, but the true test of unsupervised learning lies in production system engineering. In real-world software architecture, clustering and dimensionality reduction are not isolated academic exercises. They are critical components embedded within large-scale distributed data pipelines, search engines, cybersecurity systems, and automated decision platforms. To appreciate their impact, let us examine how these techniques solve high-stakes engineering problems across major industry verticals. Our first major application domain is computer vision, specifically image compression and color quantization using k-means clustering. A digital true color RGB image represents each pixel using three 8-bit color channels: red, green, and blue, because each channel can take 256 distinct values. A single pixel can express over 16.7 million unique colors. Storing or transmitting raw true color images across low bandwidth networks demands substantial storage and network throughput. To compress image size without altering spatial dimensions, system architects use k-means color quantization. Imagine viewing an uncompressed image containing millions of subtle color gradients. A color quantization pipeline extracts every individual pixel from the image, treating each pixel as a three-dimensional feature vector containing its red, green, and blue color coordinates in continuous space. The system then fits a k-means clustering model on these three-dimensional vectors, setting k to a modest number such as 16, 32, or 64. Lloyd's algorithm partitions the 16.7 million possible colors into k-dense clusters, finding k-optimal centroid vectors that represent the geometric average colors of the most dominant visual clusters in the image. Once centroids are computed, every original pixel in the image is replaced by the index of its nearest centroid. Instead of storing 24 bits of raw color data per pixel, the image file stores a color palette table containing the k RGB centroid vectors, plus a lightweight index matrix where each pixel requires only 4 to 6 bits to reference its assigned palette index. This simple vector quantization pipeline achieves dramatic compression ratios, often reducing file size by 60 to 80%, while preserving visual clarity. Similar vector quantization techniques form the core of audio codecs, video compression algorithms, and neural network weight quantization pipelines. Our second major application domain is cybersecurity, financial fraud prevention, and system health monitoring through anomaly detection. In high-throughput electronic payment networks or cloud infrastructure logging platforms, identifying suspicious fraudulent transactions or failing microservice nodes requires real-time anomaly detection. Supervised classification often fails in these environments because novel attack patterns emerge continuously without pre-existing training labels, and fraudulent events constitute less than 0.01% of total traffic, creating extreme class imbalance. Unsupervised clustering and PCA provide highly effective, self-contained solutions for anomaly detection. Using density-based clustering like DBSCAN or DBSCAN, system engineers feed real-time telemetry feature vectors, such as transaction amounts, geospatial velocity, API request frequency, and device fingerprint hashes into the model. Because DBSCAN naturally isolates points that fall outside dense epsilon neighborhoods, any incoming transaction classified as a noise point, assigned a cluster label of -1, is flagged instantly as a potential anomaly. The system routes these noise points to high-priority manual review queues or triggers automated secondary authentication challenges. Alternatively, systems use PCA-based reconstruction error for high-dimensional anomaly detection. The system trains a PCA model on a historical baseline of normal operating telemetry. Because the PCA model is fit on valid traffic, its top principal components capture the normal correlation structure of healthy system operations. When a new telemetry vector X arrives, the system projects X onto the top principal components and immediately reconstructs it back to original space as X hat. If the incoming request follows normal system patterns, its features align with the principal components, resulting in a tiny reconstruction error. However, if an attacker attempts an uncharacteristic exploit, such as an unannounced database dump or a credential stuffing campaign, the anomalous vector contains feature combinations that lie orthogonal to the principal components. The reconstruction error surges past a predefined statistical threshold, triggering real-time alerts. This PCA reconstruction anomaly mechanism operates inside modern intrusion detection systems, industrial sensor monitoring platforms, and credit card fraud prevention engines. Our third major application domain is bioinformatics, genomics, and gene expression analysis using hierarchical clustering. In modern biological systems engineering and personalized medicine, microarrays and high-throughput sequencing platforms measure the expression levels of tens of thousands of genes across hundreds of tissue samples. Discovering which genes act together in regulatory networks or identifying distinct cancer subtypes requires uncovering multi-scale hierarchical relationships within massive gene expression matrices. Bioinformatics pipelines apply agglomerative hierarchical clustering with wards or average linkage to both rows and columns of gene expression matrices, a technique known as biclustering. By clustering rows, the system groups genes that exhibit correlated expression patterns across samples, revealing functional co-regulated gene modules. By clustering columns, the system groups tissue samples that share similar genetic profiles, discovering previously unknown disease subtypes without clinical labels. The output is visualized as a clustered heat map, where horizontal and vertical dendrograms reorder the matrix rows and columns to bring dense co-expressed blocks together. This hierarchical biclustering framework has driven major discoveries in oncology, pharmacology, and synthetic biology. Our fourth major application domain is natural language processing, document organization, and automated topic discovery using spherical clustering and embedding spaces. Modern enterprise knowledge management platforms ingest millions of unstructured documents, customer support tickets, and legal contracts daily. Organizing these documents into coherent topic hierarchies manually is impossible. Systems automate this using document clustering pipelines. First, raw text documents are transformed into dense mathematical vectors using deep language model embeddings or sparse term frequency inverse document frequency, known as TF-IDF feature vectors. Sparse TF-IDF vectors capture word frequency importance, while neural embeddings capture semantic context. Because text feature vectors operate in high-dimensional sparse spaces where document length creates large magnitude variations, standard Euclidean k-means performs poorly. Systems utilize spherical k-means or cosine distance wards hierarchical clustering. Spherical k-means projects all document embedding vectors onto a unit hypersphere, grouping documents based on directional semantic alignment rather than raw word counts. By extracting the top terms or embedding dimensions nearest to each cluster centroid, the system automatically assigns human-interpretable topic labels to each cluster, such as billing inquiries, technical support, or feature requests. This document clustering pipeline powers automated ticket routing in enterprise customer support desks, news aggregation engines, and legal discovery platforms. Now let us examine the operational system architecture required to run clustering algorithms in large-scale production environments. In enterprise software engineering, clustering workflows are split into two distinct operational phases: offline batch training and online real-time inference. Offline batch training pipelines run on distributed computing frameworks, executing model fitting across terabyte-scale historical datasets. The training job ingests raw data, executes feature normalization, runs hyperparameter sweeps using Silhouette or Kolinsky-Harabass metrics, and exports trained cluster centroids, PCA projection matrices, or graph indices to a centralized model registry. Online real-time inference pipelines consume high-throughput event streams from message brokers. When an incoming data point arrives, the inference service cannot afford to refit the clustering model across the entire historical dataset. It must assign the incoming point to an existing cluster within low-latency service-level agreements, typically under 10 milliseconds. For centroid-based models like k-means or linear PCA, online inference is computationally light. The service simply standardizes the incoming vector, computes Euclidean distances to the stored centroid vectors, and assigns the point to the nearest centroid. However, for dense embedding spaces containing millions of item vectors, such as real-time recommendation engines searching for similar product clusters, calculating exact Euclidean or cosine distance across millions of candidate vectors introduces severe latency bottlenecks. To achieve sub-millisecond real-time inference at scale, production architectures integrate vector databases and approximate nearest neighbor, or ANN search engines. Vector databases such as FAISS, HNSLib, Milvus, or Quadrant build specialized spatial graph indices over high-dimensional vector embeddings. The dominant indexing framework is hierarchical navigable small world graphs, known as HNSW. HNSW constructs a multi-layer graph hierarchy over vector embeddings, similar to a skip-list data structure. The top layers contain sparse long-range connections for fast course navigation across space, while bottom layers contain dense local connections for precise spatial targeting. In addition to HNSW, systems utilize inverted file indexing with product quantization, or IVFPQ, which segments high-dimensional spaces into Voronoi cells and quantizes subvector spaces into lightweight bytes. SCANN and ANOI algorithms provide additional tree and vector projection acceleration. When an online query vector arrives, the vector database navigates the HNSW graph hierarchy from top to bottom, finding the nearest cluster centroids or vector neighbors in logarithmic time complexity, big O of log n, rather than scanning the full dataset in linear big O of n time. Finally, production system architects must continuously manage model drift and cluster stability. In dynamic operational environments, data distributions evolve over time, a phenomenon known as population drift or concept drift. In customer segmentation, consumer spending habits shift due to macroeconomic changes. In fraud detection, attackers modify their tactics to evade existing rules. Over time, static cluster centroids become stale, degrading segmentation quality and inference accuracy. To maintain system health, production architectures implement automated model monitoring pipelines. The system tracks statistical distribution metrics, such as the Population Stability Index or PSI, and tracking mean silhouette scores over sliding time windows. If the Population Stability Index exceeds a defined threshold or if average reconstruction error surges on normal traffic, the monitoring engine triggers automated reclustering pipelines, refitting centroids on recent data windows and deploying updated model artifacts seamlessly to production-serving infrastructure. In summary, real-world unsupervised learning is a dynamic engineering discipline. From image color quantization and cybersecurity anomaly detection to genomic biclustering, automated topic discovery, and vector database real-time inference, clustering and dimensionality reduction serve as foundational building blocks for intelligent enterprise software systems. To tie together our theoretical understanding of clustering, dimensionality reduction, and system architecture, let us walk through a comprehensive, end-to-end industrial case study. Building an enterprise customer segmentation engine for a global e-commerce and digital services platform processing tens of millions of user accounts. In modern e-commerce enterprises, treating every customer identically with generic marketing, uniform user interfaces, and static recommendation algorithms results in poor engagement and high customer churn. Marketing teams need to understand organic customer personas to tailor promotional campaigns. Product teams need to customize app onboarding flows based on user behavior, and finance teams need to identify high-value account segments to optimize customer acquisition costs. Because customer behavior is continuous, multidimensional, and constantly evolving, static manual rules fail. The organization requires an automated, data-driven, unsupervised customer segmentation engine. Let us trace the complete architectural lifecycle of this production system, from raw data ingestion and feature engineering to model benchmarking, cluster interpretation, and production lifecycle monitoring. The first architectural phase is data ingestion and feature extraction. Raw customer interaction data streams into data lakes from multiple transactional databases, clickstream event collectors, and customer support databases. The feature engineering pipeline aggregates these raw event logs over a rolling 90-day window, constructing a comprehensive multidimensional feature vector for each customer. At the core of customer behavioral modeling is the classical RFM framework, augmented with modern digital telemetry features and tenure tracking, known as RFMT. RFM stands for recency, frequency, and monetary value. Recency measures the number of days elapsed since the customer's last purchase or active app session. Frequency measures the total number of completed transactions within the rolling window. Monetary value measures the total net revenue generated by the customer over that same period. Tenure tracks the total account age in days. To capture digital engagement beyond raw transactions, the pipeline extracts advanced behavioral telemetry features. These include average session duration, measure of time spent per app visit, cart abandonment rate, ratio of initiated shopping carts to completed checkouts, device diversity, number of distinct operating systems and hardware platforms used to access the account, discount sensitivity, proportion of purchases made using promotional discount codes, and category browsing entropy, A statistical entropy metric measuring whether a customer browses a narrow, specialized product category or explores a wide, diverse spectrum of merchandise. Once raw features are extracted, the pipeline enters a critical pre-processing stage: distribution transformation and normalization. In real-world customer data, behavioral features almost never follow a clean Gaussian bell curve. Features like monetary value, transaction frequency, and session duration exhibit extreme right-skewed, power law distributions. A tiny fraction of power buyers generate millions of dollars in revenue and thousands of transactions, while the vast majority of users make one or two small purchases. If you feed untransformed right-skewed data directly into Euclidean distance-based algorithms like k-means, the extreme power law tail distorts distance calculations completely. The algorithm will isolate a handful of massive whales into tiny singleton clusters while squashing 99% of normal customers into a single massive, uninterpretable cluster blob. To resolve severe feature skewness, the pre-processing pipeline applies power transformations. For strictly positive feature variables, the pipeline applies a logarithmic transformation, taking the natural log of 1 plus the feature value. The logarithmic function compresses vast numerical ranges, turning values spanning across orders of magnitude into a compact linear scale. For features containing 0 or negative values, the pipeline applies the Yeo-Johnson transformation, a parametric power transformation that stabilizes variance and minimizes skewness across arbitrary real-valued distributions. Following power transformations, features must be normalized onto a common numerical scale. If features possess extreme residual outliers, standard zero-mean unit variance scaling can still be distorted because standard deviation calculations are sensitive to extreme values. The pipeline utilizes robust scaling or quantile transformation. Robust scaling subtracts the median of each feature and divides by the interquartile range, the difference between the 75th and 25th percentiles, ensuring that outlier values do not distort the scaling parameters. Quantile transformation maps features onto a uniform or normal distribution using empirical cumulative distribution functions, providing complete immunity to extreme outliers. With a clean, transformed, standardized feature matrix in hand, the system enters the second architectural phase, model selection and algorithm benchmarking. Rather than blindly selecting a single clustering algorithm, robust software engineering requires constructing an automated benchmarking pipeline that fits and compares multiple clustering paradigms concurrently. In our customer segmentation system, the benchmarking suite evaluates 3 core algorithmic candidates: k-means++, agglomerative hierarchical clustering with Ward's linkage, and Gaussian mixture models, known as GMMs. Let us explore Gaussian mixture models in technical detail, as GMMs provide a powerful probabilistic generalization of k-means. While k-means performs hard assignment using spherical Euclidean distances, a Gaussian mixture model assumes that the dataset is generated by a mixture of k underlying Gaussian probability distributions, each with its own mean vector, covariance matrix, and mixture weight coefficient. GMMs perform soft clustering, assigning each customer a continuous probability vector representing their likelihood of belonging to each of the k segments. Furthermore, GMMs support flexible covariance structures. Spherical covariance assuming equal variance in all directions, diagonal covariance assuming feature independence, tied covariance assuming all clusters share a common covariance shape, and full covariance allowing each cluster to form an elongated, arbitrarily oriented hyperellipsoid. A Gaussian mixture model is trained using the expectation maximization or EM algorithm. In the expectation step, The model fixes the current Gaussian parameters and computes the posterior probability of each data point belonging to each Gaussian distribution. In the maximization step, the model updates the mean vectors, covariance matrices, and mixture weights of each Gaussian distribution using the weighted observations from the expectation step. This two-step loop iterates until log likelihood convergence. To select the optimal algorithm and the optimal number of customer segments K, the benchmarking pipeline executes an automated hyperparameter grid search across K values ranging from 2 to 15. The pipeline records multiple validation metrics across the grid search: the mean silhouette coefficient, the Davies-Bouldin index, the Kolinsky-Harabass index, and for Gaussian mixture models, the Bayesian Information Criterion or BIC and Akaike Information Criterion or AIC. The Bayesian Information Criterion penalizes model complexity, the number of parameters in the covariance matrices, against log likelihood fit. A sharp drop in BIC followed by an elbow curve indicates the optimal probabilistic model complexity. By synthesizing validation scores, the benchmarking pipeline selects the winning model configuration. A 5-cluster k-means plus model initialized with robust scaled features, which achieves the peak silhouette score and minimal Davies-Bouldin index while producing highly distinct, balanced segment sizes. The third architectural phase is cluster interpretation and persona extraction. A clustering model is useless to an enterprise if its output is merely a list of arbitrary integer cluster IDs from 0 to 4. System engineers must translate mathematical cluster centroids into actionable business personas. To extract interpretable cluster profiles, the system calculates the mean and median values of the original, untransformed feature variables across each discovered cluster, comparing segment averages against global baseline population means. Let us inspect the 5 discovered customer segments. Segment 0 represents the high-value VIP power buyers. This cluster comprises approximately 8% of total users but generates over 45% of total platform revenue. Centroid analysis reveals extremely low recency, averaging less than 2 days since last purchase, extremely high frequency, high monetary spend, low cart abandonment rate, and very low discount sensitivity. These customers are loyal power users who buy regularly at full price. Segment 1 represents the at-risk churn candidates. This segment comprises 15% of users who previously exhibited high transaction frequency and spend, but whose recency metric has surged to over 60 days of inactivity. Their category browsing entropy has collapsed, and their app login frequency has dropped sharply. These are formerly valuable customers who are actively disengaging from the platform. Segment 2 represents the bargain-hunting promo seekers. This segment comprises 27% of users characterized by moderate frequency and low monetary spend, but possessing an extremely high discount sensitivity score. Over 85% of their transactions involve promotional coupon codes or flash sale items. Their recency drops during major holiday sales events but remains flat during full price periods. Segment 3 represents the high-volume window shoppers. This segment comprises 32% of total accounts. Centroid analysis shows high. Segment 4 represents the recent casual buyers. This cluster comprises 18% of users characterized by very low recency, having made their first purchase within the last 14 days, low overall frequency, and moderate basket size. They represent newly acquired users whose long-term retention trajectory is undetermined. The fourth architectural phase is system integration and automated business workflows. Once customer personas are validated, The model pipeline exports cluster centroid artifacts to the production model store and executes bulk batch inferencing, tagging every user account in the enterprise data warehouse with their assigned cluster segment ID and segment probability distribution. Automated downstream microservices consume these segment tags to trigger tailored operational workflows. The marketing automation engine ingests segment tags daily. When a user is tagged in segment 1, at-risk churn candidates, an automated re-engagement campaign fires, sending personalized win-back offers and dedicated customer support outreach. When a user is tagged in segment 2, bargain hunters, they receive notifications exclusively during promotional discount events. The real-time recommendation engine reads segment tags during active app sessions. For segment 0 VIP power buyers, the user interface emphasizes premium new product arrivals and exclusive loyalty rewards. For segment 3, high-volume window shoppers, the onboarding interface displays targeted checkout incentive banners and simplified one-click payment options to convert browsing behavior into completed purchases. The fifth and final architectural phase is production monitoring and lifecycle management. In dynamic consumer markets, customer behavior drifts continuously. To prevent model degradation, the monitoring service tracks Population Stability Index, or PSI, weekly, comparing current customer feature distributions against the baseline distributions recorded during model training. By incorporating Markov chain transition matrices across customer cluster states over consecutive 90-day windows, the system predicts customer migration trajectories, identifying users transitioning from VIP power buyers to at-risk candidates before churn occurs. If macroeconomic shifts or product UI redesigns cause the Population Stability Index to exceed 0.25, signaling significant population drift, the monitoring pipeline flags the current model as degraded and automatically triggers a retraining workflow, re-executing feature transformation, hyperparameter grid search, and centroid extraction across the latest 90-day data window. In summary, this customer segmentation case study illustrates how unsupervised learning transforms raw, unlabeled behavioral logs into a strategic enterprise engine. By unifying robust data transformation, multi-algorithm benchmarking, probabilistic GMM modeling, centroid profile interpretation, vector database integration, transition matrix modeling, and automated monitoring, software engineers build resilient, business-critical machine learning systems. When software engineers transition from low-dimensional toy datasets to high-dimensional production feature spaces, they encounter counterintuitive mathematical phenomena that defy human physical intuition. In 3 dimensions, we live in a world where spatial distances are informative, volumes expand predictably, and the center of an object contains most of its bulk. But as feature spaces expand into hundreds or thousands of continuous dimensions, geometric rules warp completely. Space becomes unimaginably vast, incredibly sparse, and weirdly hollow. This suite of mathematical pathologies is known collectively as the curse of dimensionality. Understanding the curse of dimensionality is essential for any machine learning system architect. Failing to account for high-dimensional geometry causes clustering models to fail, distance metrics to lose diagnostic meaning, and computational resource consumption to explode. Let us explore the geometric paradoxes of high-dimensional space, analyze why standard distance metrics break down, examine computational scaling bottlenecks, and establish a comprehensive engineering best practices checklist. Our journey begins with the strange geometry of high-dimensional hyperspheres and hypercubes. To build intuitive visual models, Consider comparing a two-dimensional square with a high-dimensional unit hypercube. In 2 dimensions, a unit square has sides of length 1 and an area of 1. If you place a unit circle inside the square, touching all 4 walls, the circle occupies approximately 78.5% of the total area of the square. The corners of the square contain only 21.5% of the total area. Now, expand this geometric setup into a d-dimensional space. Imagine a d-dimensional unit hypercube with side length 1, containing an inscribed d-dimensional hypersphere of radius 0.5 touching all sides of the hypercube. What fraction of the hypercube's volume does the inscribed hypersphere occupy as the dimension d increases? In 3 dimensions, the inscribed sphere occupies 52.4% of the cube's volume. In 8 dimensions, the hypersphere occupies less than 2.5% of the cube's volume. By the time dimensions expand to 20, the volume of the inscribed hypersphere drops to 0.03% of the hypercube's volume. Where did all the volume go? In high-dimensional space, virtually all the volume of a hypercube concentrates in its distant corners. The central region of space is essentially empty. A high-dimensional hypercube is not a solid block like a 3D brick. It resembles a hollow, spiky sea urchin where long narrow spikes extend into the corners while the interior center contains almost zero volume. An equally shocking geometric paradox occurs when examining the volume distribution of a high-dimensional hypersphere itself. Consider a d-dimensional hypersphere of radius r. Imagine cutting away a thin outer shell of thickness epsilon from the outer surface of the sphere. What fraction of the sphere's total volume resides within that thin outer skin compared to its solid interior core? The volume of a d-dimensional hypersphere scales proportionally to its radius raised to the power of d. The ratio of the volume of the inner core of radius r minus epsilon to the total volume of radius r equals 1 minus epsilon divided by r, all raised to the power of d. As the dimension d approaches infinity, this ratio approaches 0 exponentially. This mathematical limit reveals a profound truth. In high-dimensional space, virtually 100% of the total volume of a hypersphere resides within a paper-thin outer shell immediately beneath its surface. The interior core of a high-dimensional sphere is completely hollow. These volume concentration paradoxes lead directly to the most destructive pathology for clustering algorithms: the distance concentration phenomenon. In low-dimensional space, spatial distance provides strong diagnostic contrast. If you select a data point at random in 3-dimensional space, some neighboring points will sit very close to it, while other points will sit far away. The ratio of the distance to the furthest point divided by the distance to the nearest point is large. However, as the dimension d approaches infinity, theoretical proofs demonstrate that under mild statistical independence assumptions, the distance between any pair of points in high-dimensional space converges to a constant value. The variance of pairwise distances fails to grow at the same rate as the magnitude of the mean distance. Mathematically, the difference between the maximum Euclidean distance from a reference point to any other point in the dataset and the minimum Euclidean distance shrinks to near zero relative to the minimum distance itself. In a 100-dimensional space, every single data point is almost exactly the same distance away from every other data point. Imagine trying to run k-means, agglomerative hierarchical clustering, or DBSCAN in a feature space where every pair of points is mutually equidistant. K-means cannot find meaningful centroids because assignment steps produce arbitrary Voronoi cells based on floating point rounding noise. Single linkage hierarchical clustering suffers total chaining breakdown because all pairwise distances are identical. DBSCAN fails because every point either has zero neighbors within epsilon or includes the entire dataset within epsilon. An additional high-dimensional pathology is the hubness problem. In high-dimensional spaces, certain data points, called hubs, emerge as nearest neighbors to disproportionately large numbers of other points across the dataset, distorting nearest neighbor graph topologies. To mitigate the distance concentration phenomenon and hubness, engineers must evaluate how different distance metrics behave as dimensions grow. The standard Euclidean distance, or L2 norm, measures straight-line distance by summing squared coordinate differences and taking the square root. Because Euclidean distance squares coordinate differences, it is extremely sensitive to large dimensional variances, making it the most vulnerable distance metric to the distance concentration phenomenon in high-dimensional spaces. The Manhattan distance, or L1 norm, measures distance by summing the absolute differences along individual coordinate axes. Theoretical and empirical studies demonstrate that the L1 norm preserves significantly higher relative distance contrast than the L2 norm as dimensionality increases, making Manhattan distance a far more robust choice for high-dimensional clustering. Going further, researchers use fractional norms, or LP norms, where p is a fraction between 0 and 1. A fractional norm sums coordinate differences raised to a fractional power p, such as 0.5. Fractional norms preserve even higher relative contrast in high-dimensional spaces than Manhattan distance, though they violate the triangle inequality and do not form a strict metric space. In sparse high-dimensional domains, such as text processing or gene expression vectors, engineers replace spatial distance metrics entirely with cosine similarity or angular distance. Cosine similarity measures the cosine of the angle between two feature vectors, ignoring magnitude variations completely. Because cosine similarity evaluates directional alignment rather than spatial distance, it is completely immune to hypervolume concentration, providing robust similarity scoring across thousands of sparse feature dimensions. To learn metric spaces custom-fitted to domain manifolds, engineers use metric learning techniques, such as neighborhood components analysis or large margin nearest neighbor, which learn Mahalanobis projection matrices directly from data. Now let us examine the computational bottlenecks associated with high-dimensional spatial processing. The first bottleneck is memory footprint. As discussed in our analysis of hierarchical clustering and DBSCAN, computing exact pairwise distance matrices requires big O of n-squared memory storage. When feature vectors expand to thousands of dimensions, calculating and caching an n-by-n distance matrix for 100,000 observations requires tens of gigabytes of RAM, overwhelming system caches and causing severe memory thrashing. The second bottleneck is spatial tree degradation. In low-dimensional spaces, nearest neighbor queries run efficiently in logarithmic time using spatial indexing trees like KD trees or R trees. A KD tree recursively partitions space along individual coordinate axes, allowing search algorithms to prune vast branches of the search space. However, as dimensionality D increases past 20 or 30, spatial indexing trees collapse completely. Because volume concentrates in corners and all points sit equidistant on hypersurfaces, the bounding boxes of tree nodes overlap continuously. The search algorithm can no longer prune branches safely, forcing the KD tree to inspect virtually every single node in the tree. The query time degrades from logarithmic big O of log n back to brute force linear scanning, big O of n times d. To maintain subquadratic scalability in high-dimensional production systems, Engineers replace exact spatial search with approximate nearest neighbor, or ANN search strategies. Approximate nearest neighbor algorithms trade a tiny fraction of search accuracy, say achieving 99% recall, for orders of magnitude faster query throughput. Three dominant ANN frameworks power high-dimensional production architectures. First is locality-sensitive hashing, or LSH. LSH uses specialized hash functions that deliberately cause collisions for points that sit close together in feature space. By hashing feature vectors into bucket indices, LSH reduces nearest neighbor search to scanning a small candidate bucket, executing in sublinear time. Second is inverted file indexing with product quantization, known as IVFPQ, popularized by the FACE library. Product quantization breaks a high-dimensional vector into smaller subvectors, clusters each subvector space using k-means, and replaces subvectors with short quantization codes. Pairwise distances are computed instantly using pre-computed lookup tables, reducing memory usage by 90% while dramatically accelerating search speed. Third is hierarchical navigable small world graphs, or HNSW, which build multi-layer proximity graphs across vector space, enabling logarithmic search navigation. To navigate these high-dimensional challenges successfully, system architects follow a comprehensive best practices checklist. First, mandatory pre-processing and scaling. Never feed raw, unscaled features directly into distance-based clustering models. Apply standard scaling or robust median scaling to ensure equal feature representation. Second, dimensionality reduction before clustering. When operating in spaces with dozens or hundreds of continuous features, always execute dimensionality reduction prior to clustering. Apply PCA to eliminate multicollinearity and compress linear variance, or train a denoising autoencoder to project features onto a clean, lower-dimensional nonlinear manifold before running k-means or DBSCAN. Reducing dimensions from 500 down to 20 eliminates distance concentration while accelerating model training by orders of magnitude. Third, outlier removal and noise isolation. Outliers exert disproportionate distortion on centroid-based models. Use isolation forests, local outlier factors, or DBSCAN noise isolation to prune extreme outliers from training sets before fitting final cluster models. Fourth, metric matching domain geometry. Match your distance metric to the geometric properties of your feature space. Use Euclidean distance for low-dimensional continuous physical spatial data, Manhattan distance for moderate-dimensional continuous data, cosine similarity for high-dimensional sparse text vectors, and Mahalanobis distance when features exhibit strong correlation structures. Fifth, multimetric interpretability validation. Never evaluate clustering quality using a single internal metric. Synthesize silhouette scores, Davies-Bouldin indices, Kolinsky-Harabass ratios, Dunn indices, and stability bootstrapping tests to confirm that discovered clusters reflect genuine structural phenomena rather than mathematical noise. To consolidate everything we have explored throughout this masterclass, from k-means variance, hierarchical trees, and density-based DBSCAN to PCA derivations, t-SNE, UMAP, autoencoders, evaluation metrics, and high-dimensional geometry, we will now walk through a complete, hands-on, end-to-end software engineering project. We will architect, build, evaluate, and deploy an enterprise-grade unsupervised machine intelligence engine for a global multi-tenant cloud infrastructure and Internet of Things telemetry platform. Imagine operating a cloud enterprise platform that manages millions of connected edge devices, microservices, and user sessions across global data centers. Every second, millions of continuous telemetry events stream into the platform, capturing CPU utilization, memory allocation, disk input-output rates, network packet velocity, API error distributions, security token access patterns, and user session interaction sequences. Operating this platform presents two major software engineering challenges. First, system operations teams need to detect anomalous microservice failures, hardware degradations, and zero-day security intrusions in real time without relying on static manual threshold rules. Second, product and infrastructure teams need to group edge nodes and user workloads into natural behavioral clusters to optimize workload scheduling, auto-scaling policies, dynamic routing, and multi-tenant resource pricing. Because incoming telemetry streams contain hundreds of continuous, correlated, and noisy features arriving without ground truth labels, supervised learning cannot solve these problems. We must build a fully automated, self-contained, unsupervised machine learning pipeline. Let us walk through the architecture of this production system step by step, following the complete software engineering lifecycle from raw data ingestion and feature engineering to dimensionality reduction, multi-algorithm clustering benchmarks, cluster profile interpretation, vector database integration, and continuous production lifecycle monitoring. The first phase of our project is ingestion architecture and feature pipeline engineering. Telemetry data originates from lightweight monitoring agents installed on thousands of cloud servers and edge IoT devices. These agents stream continuous JSON telemetry payloads into an Apache Kafka message broker cluster. The Kafka stream is consumed by a distributed stream processing framework, which buffers incoming events into sliding 10-minute aggregation windows. For each server node and active user account during a 10-minute window, the feature extraction pipeline calculates a multidimensional feature vector containing 48 continuous metrics. These features include compute metrics such as mean CPU load, peak memory consumption, and context switch frequency. Network metrics such as inbound packet volume, outbound bandwidth, and connection retries. Storage metrics such as disk read latency and write throughput. Security metrics such as failed authentication rate, token rotation velocity, and geolocation distance jump. And application metrics such as API request rate, error 53 frequency, and session duration entropy. As these 48 raw feature vectors exit the stream aggregator, the pipeline subjects them to rigorous data cleaning and missing value imputation. In real-world IoT and cloud monitoring streams, network drops and server reboots cause missing values. The pipeline uses k-nearest neighbors imputation. For any feature vector containing missing entries, the imputer calculates Euclidean distances to candidate complete vectors within the current sliding window, identifies the 5 nearest neighbor vectors, and imputes the missing entries using the weighted average of those neighbors. This preserves local correlation structures far better than naive mean or median filling. Next, the pipeline addresses extreme feature skewness and heavy-tailed distributions. Inspecting raw telemetry metrics reveals that features like network bandwidth, disk write throughput, and failed authentication rates exhibit severe right-skewed power law distributions. 95% of healthy edge nodes exhibit low, steady network bandwidth, while a tiny fraction of heavy streaming nodes or distributed denial-of-service targets consume gigabits per second. If we pass untransformed raw features directly into distance calculations, the immense numerical scale of bandwidth metrics will completely swamp subtle variations in CPU load or error rates. To eliminate skewness across all 48 features automatically, the pipeline applies the Yeo-Johnson transformation to every feature column. The Yeo-Johnson transformer calculates an optimal power parameter, lambda, for each feature using maximum likelihood estimation, transforming skewed distributions into near-Gaussian symmetric bell curves while preserving zero and negative values cleanly. Following power transformation, the feature matrix passes into a robust feature scaling module. Because telemetry streams occasionally contain extreme hardware glitch outliers, standard zero-mean unit variance scaling can still suffer from inflated standard deviation estimates. The pipeline uses robust scaling, subtracting the median of each transformed feature column and dividing by its interquartile range. This guarantees that all 48 feature dimensions reside on a comparable numerical scale centered at 0, anchored securely by the middle 50% of valid operating data. With a clean, transformed, standardized 48-dimensional feature matrix prepared, our system enters the second phase, dimensionality reduction and manifold visualization. Processing 48 feature dimensions across millions of edge node records introduces computational overhead and exposes downstream clustering algorithms to mild distance concentration effects. Furthermore, infrastructure engineers demand an intuitive two-dimensional visual dashboard to monitor the global structural health of the entire server fleet. To meet both requirements, our pipeline constructs a dual dimensionality reduction pipeline, an online linear PCA compression pipeline for downstream clustering models, and an offline UMAP manifold pipeline for real-time visual dashboards. Let us trace the linear PCA pipeline first. The pipeline ingests the standardized data matrix X, consisting of n rows representing server time windows and 48 feature columns. It executes singular value decomposition on X, factorizing matrix X into left singular vectors U, singular values matrix sigma, and right singular vectors V transpose. The pipeline extracts the eigenvalues of the sample covariance matrix by squaring the singular values on the diagonal of sigma and dividing by n-1. It then computes the explained variance ratio for all 48 principal components. Analyzing the cumulative explained variance curve reveals that the first 8 principal components account for 87.4% of total variance across the dataset, while the first 12 principal components capture 94.2% of total dataset variance. The scree plot displays a clear elbow point after component 12, beyond which components represent low variance sensor noise. The pipeline constructs a 48 by 12 projection matrix containing the top 12 right singular vector columns of matrix V. Multiplying the standardized feature matrix by this projection matrix transforms our 48-dimensional space into a compact 12-dimensional linear representation, eliminating. Now let us trace the nonlinear UMAP visualization pipeline. While 12 linear PCA components preserve total variance for machine learning models, infrastructure engineers need to visualize complex, nonlinear cluster relationships on a two-dimensional monitoring screen. Linear PCA projected into 2 dimensions squashes complex curved surfaces, blending distinct failure modes into overlapping blobs. Our pipeline fits a UMAP model on a random subsample of 50,000 server feature vectors drawn from the current operational window. The pipeline configures UMAP with an n_neighbors parameter of 30 and a min_dist parameter of 0.1. An n_neighbors setting of 30 balances local neighborhood cluster details with global fleet-wide manifold topology, while a min_dist setting of 0.1 forces tight visual cluster packing. UMAP constructs a high-dimensional fuzzy simplicial set graph over the feature vectors using adaptive local metrics, and optimizes a two-dimensional low-dimensional layout using fuzzy set cross-entropy gradient descent. The resulting UMAP two-dimensional map reveals stunning visual clarity. Healthy web servers cluster into a dense, central mainland. Database nodes form a distinct adjacent cluster. Storage arrays align along an elongated continuous ridge, and anomalous compromised nodes break away into isolated, distant islands. Now our system enters the third phase: multi-algorithm clustering, benchmarking, and automated model selection. With a compact 12-dimensional PCA feature space prepared, the pipeline executes an automated benchmarking suite to discover the optimal clustering architecture for our server fleet. Rather than assuming a single algorithm fits all workloads, the benchmarking suite fits and evaluates 4 distinct clustering paradigms concurrently across identical dataset splits. Algorithm 1 is k-means plus initialization combined with Lloyd's expectation maximization algorithm. The pipeline executes a hyperparameter search, evaluating cluster counts k ranging from 2 to 20. For each k value, it runs 10 random k-means plus restarts to avoid local minima traps. Algorithm 2 is agglomerative hierarchical clustering using Ward's minimum variance linkage criterion, evaluated across k values from 2 to 20. Algorithm 3 is DBSCAN, evaluated across minimum cluster size parameters ranging from 50 to 500, and minimum points parameters ranging from 10 to 50. Algorithm 4 is a Gaussian mixture model with soft assignment, evaluated across k values from 2 to 20 using both diagonal and full covariance matrices. To evaluate and select the winning model configuration objectively, the benchmarking pipeline calculates 4 statistical validation metrics for every candidate model configuration: the mean silhouette coefficient, the Davies-Bouldin index, the Kolinsky-Harabass variance ratio criterion, and for Gaussian mixture models, the Bayesian information criterion. Let us analyze the empirical benchmark results across candidate models. For k-means plus, the mean silhouette score curve increases smoothly as k moves from 2 to 6, reaches a sharp global peak of 0.62 at k equals 6, and then drops steadily as k expands past 8. The Davies-Bouldin index achieves its minimum score of 0.58 at k equals 6, confirming that 6 clusters maximize internal compactness and intercluster separation. For agglomerative Ward's hierarchical clustering, the cophonetic correlation coefficient achieves an impressive score of 0.89. Slicing the dendrogram across its largest vertical height jump yields 6 primary branches, mirroring the k-means result. For DBSCAN, setting minimum cluster size to 200 and minimum points to 25 discovers 5 major dense clusters, while cleanly isolating 2.3% of the dataset as noise points, assigning them a label of -1. For Gaussian mixture models, the Bayesian information criterion curve drops sharply from k equals 2 to k equals 6, reaching an optimal plateau at k equals 6 with full covariance matrices, confirming that 6 probabilistic Gaussian components represent the underlying data generation process. Synthesizing these benchmark metrics, the pipeline selects the 6-cluster k-means plus model as the primary operational engine for real-time workload tiering due to its fast inference speed, linear scaling, and peak silhouette score. Concurrently, the pipeline deploys the DBSCAN model as a dedicated real-time anomaly detection service, leveraging its noise isolation capability to flag security intrusions and hardware failures. Now our system enters the 4th phase: cluster profile interpretation and operational system rules. A machine learning model that outputs arbitrary cluster numbers from 0 to 5 provides 0 value to site reliability engineers. Our pipeline translates mathematical cluster centroids into human interpretable system personas and actionable automation rules. The pipeline extracts the 12-dimensional centroid vector for each of the 6 k-means clusters and projects them back into the original 48-dimensional untransformed feature space. It computes the mean and median values of raw physical metrics across each segment, comparing cluster means against global population baselines. Let us inspect the operational personas of the 6 discovered clusters. Cluster 0 represents healthy general-purpose web application nodes. This cluster comprises 42% of the fleet. Centroid analysis shows moderate CPU load averaging 35%, low disk latency, low error rates, and normal network traffic. These nodes operate comfortably within nominal parameters. Cluster 1 represents memory-intensive in-memory cache nodes. This cluster comprises 18% of the fleet. Centroid analysis reveals high peak memory usage averaging 88%, extremely high context switch frequencies, low disk input-output, and high internal network packet rates. Cluster 2 represents storage-bound database and logging nodes. This cluster comprises 14% of the fleet. Centroid analysis shows high disk write throughput, elevated disk read latency, low CPU utilization, and steady inbound database connections. Cluster 3 represents high compute batch processing workers. This cluster comprises 12% of the fleet. Centroid analysis shows near maximum CPU utilization averaging 94%, elevated power consumption, low network interaction, and zero public API error rates. These nodes are executing heavy mathematical batch jobs. Cluster 4 represents misconfigured, over-provisioned idle nodes. This cluster comprises 9% of the fleet. Centroid analysis reveals near zero CPU load averaging 3%, minimal memory usage, zero network traffic, yet full resource allocation. These nodes waste cloud infrastructure budget. Cluster 5 represents high-risk anomaly and intrusion targets. This cluster comprises 5% of the fleet. Centroid analysis shows erratic CPU spikes, elevated failed authentication rates, abnormal geolocation jumps, surge in error 53 responses, and unusual outbound network tunneling. The system maps these discovered personas to automated operational control logic. When a node falls into cluster 4, idle nodes, an automated orchestration rule flags the node for dynamic downscaling or consolidation, freeing up cloud infrastructure capacity and saving thousands of dollars in operational costs. When a node falls into cluster 1, memory-intensive cache nodes, the autoscaling group automatically applies RAM-optimized server profiles during infrastructure provisioning. When a node is assigned to cluster 5 by k-means or flagged as a noise point by DBSCAN, an automated security policy isolates the node from the public network, revokes its active API tokens, and alerts the Security Operations Center in real time. Now our system enters the 5th phase: production deployment, vector database integration, and real-time inference architecture. To serve low-latency cluster assignments to real-time microservices, the project implements a hybrid deployment framework combining high-throughput batch scoring with real-time vector database inference. The training pipeline runs as a nightly batch job on a distributed Spark cluster. It ingests historical telemetry logs, fits feature transformers, updates PCA projection matrices, fits k-means centroids, and exports model artifacts to a MLflow model registry. For online real-time inference, an incoming microservice telemetry payload must be assigned to a cluster segment within a 5 millisecond latency budget. To achieve this low latency threshold, our production inference service utilizes an HNSW vector database. During model deployment, the inference service takes the 6 48-dimensional centroid vectors, projects them into the 12-dimensional PCA space, and indexes them inside an HNSW graph index. When a real-time telemetry vector X arrives at the API gateway, the inference service standardizes X using stored robust scaling parameters, projects X into 12 dimensions using the PCA matrix, and queries the HNSW index. The HNSW vector database navigates its hierarchical skip graph layout, finding the nearest centroid vector and returning the cluster assignment in less than 1.2 milliseconds, easily beating our 5 millisecond SLA. Finally, our system enters the 6th phase, continuous lifecycle monitoring and automated drift retraining. In dynamic cloud environments, server software versions update, hardware architectures evolve, and user traffic patterns shift. Static cluster centroids degrade over time. Our monitoring service continuously tracks Population Stability Index, or PSI, across all 48 features on a rolling weekly basis, comparing incoming production telemetry distributions against the training baseline. If the Population Stability Index for key metrics exceeds 0.25, or if the average fleet-wide silhouette coefficient drops below 0.50, the monitoring service triggers an automated workflow. The system provisions an ephemeral training cluster, reruns Yeo-Johnson feature transformations, executes hyperparameter sweeps, refits PCA and k-means models, generates updated centroid profile reports, and deploys the refreshed model container without downtime. This completes our hands-on unsupervised project. We have built an end-to-end machine intelligence engine that ingests raw telemetry, cleans and normalizes heavy-tailed features, compresses dimensions via PCA and UMAP, selects optimal cluster counts using silhouette and BIC metrics, translates mathematical centroids into operational automation rules, serves real-time predictions via HNSW vector databases, and maintains long-term health through automated drift monitoring. Now let us step back and summarize the core engineering mindset that unites all unsupervised learning techniques explored across this masterclass. Mastering machine learning is not about memorizing API syntax or blindly running algorithms. It is about understanding systems, constraints, geometric trade-offs, and failure modes. When faced with unlabeled data, always start by asking fundamental architectural questions. What is the underlying geometry of the feature space? Are clusters spherical and convex, favoring k-means and Ward's linkage, or are they non-spherical continuous manifolds, requiring DBSCAN, optics, dpclust, or DBSCAN? What is the density distribution? Is local density uniform, or does it vary across regions, dictating the choice between flat DBSCAN and hierarchical DBSCAN? What are the dimensionality constraints? Are features low-dimensional and physical or high-dimensional and sparse, requiring PCA compression, L1 Manhattan metrics, cosine similarities, or autoencoder bottleneck embeddings? How will model quality be validated? Have you combined silhouette analysis, Davies-Bolden scores, Kolinsky-Harabass ratios, done indices, and stability bootstrapping to confirm structural validity? How will the model operate in production? Have you designed low-latency inference pathways using HNSW vector databases and implemented population stability index tracking to manage model drift over time? By reasoning through these trade-offs with technical rigor, spatial intuition, and empirical discipline, you transform unsupervised learning from abstract mathematical theory into resilient, high-impact enterprise software systems. You now possess the complete mental models, mathematical foundations, and architectural frameworks to design, build, and master state-of-the-art clustering, PCA, and dimensionality reduction systems. To deepen our mathematical understanding of k-means optimization, let us examine the formal convergence proof of Lloyd's algorithm on continuous inertia surfaces. In the assignment step, fixing centroid vectors and minimizing Euclidean distance to each data point isolates individual observations, reducing the total inertia sum term by term. In the update step, taking the partial derivative of the cluster inertia with respect to the centroid vector and setting it to 0 yields the exact component-wise arithmetic mean. Because the arithmetic mean is the unique global minimizer of squared Euclidean distances for any set of vectors, every update step strictly non-increases the objective function. Because there are a finite number of partitions of endpoints into k-clusters, the algorithm must terminate in a finite number of iterations. When implementing k-means in high-throughput distributed systems, engineers must also analyze the computational trade-offs of bisecting k-means. Bisecting k-means starts with a single cluster containing all data points and iteratively applies two-means clustering to split clusters until k-clusters are formed. At each step, bisecting k-means selects the cluster with the largest total within cluster sum of squares variance to split. This top-down binary splitting approach is computationally efficient, scaling in big O of n times k times d time, and is significantly less sensitive to initial centroid placement than standard Lloyd's algorithm. Furthermore, when evaluating soft cluster boundaries, fuzzy c-means provides a probabilistic membership framework. Instead of assigning each point to a single cluster with a binary membership of 0 or 1, fuzzy c-means assigns a membership probability to each cluster, such that the probabilities sum to 1 across all k-clusters. The cluster centers in fuzzy c-means are updated as weighted averages, where each point's contribution is weighted by its membership probability raised to a fuzzifier exponent m. As m approaches 1, fuzzy c-means converges to standard hard k-means, whereas higher values of m produce smoother, overlapping cluster boundaries suitable for ambiguous customer or biological data. To understand how hierarchical clustering updates distance matrices after each merge event, we analyzed the Lance-Williams recurrence formula in complete technical detail. The Lance-Williams formula provides a unified mathematical equation for updating the distance between an existing cluster K and a newly merged cluster formed by combining clusters I and J. The updated distance is expressed as a linear combination of the distance between I and K, the distance between J and K, the distance between I and J, and the absolute difference between the distance from I to K and the distance from J to K, weighted by coefficients alpha I, alpha j, beta, and gamma. By adjusting these four Lance-Williams coefficients, high-performance software libraries implement all major linkage criteria within a single unified matrix update loop. For single linkage, alpha I equals 0.5, alpha j equals 0.5, beta equals 0, and gamma equals negative 0.5, which simplifies directly to the minimum distance. For complete linkage, gamma equals positive 0.5, which simplifies directly to the maximum distance. For group average linkage, alpha I equals the size of cluster I divided by the combined size of I and j. Alpha j equals the size of cluster j divided by the combined size of I and j, and beta and gamma equals 0. For Ward's minimum variance linkage, alpha I equals the sum of the sizes of cluster I and cluster K divided by the total size of clusters I, J, and K, allowing constant time variance updates. In addition to Lance-Williams recurrences, Hierarchical dendrograms impose a mathematical ultrametric space on the feature domain. An ultrametric space satisfies a strengthened triangle inequality. For any 3 points x, y, and z, the cophonetic distance between x and z is less than or equal to the maximum of the cophonetic distance between x and y and the cophonetic distance between y and z. This ultrametric property guarantees that all triangles formed by cophonetic distances are isosceles with the two longer sides equal in length, producing structured nested cluster trees. To master density-based clustering, system engineers must understand the mathematical mechanics of optics and density peaks clustering. Optics, standing for ordering points to identify the clustering structure, addresses the uniform density limitation of DBSCAN by generating an augmented reachability ordering of the dataset. Optics defines the core distance of a point P as the minimum epsilon distance required for P to satisfy the minimum points threshold. It defines the reachability distance of a point P relative to a core point Q as the maximum of the core distance of Q and the spatial Euclidean distance between P and Q. By processing points through a priority queue ordered by reachability distance, optics outputs a continuous reachability plot. In a reachability plot, valleys represent dense clusters, while peaks represent sparse background noise. Slicing the reachability plot at different height thresholds allows an engineer to extract clusters across multiple density scales simultaneously. Density peaks clustering, or dpclust, provides another powerful density paradigm based on the decision graph method. dpclust assumes that cluster centers are surrounded by neighbors with lower local density and are situated at a relatively large distance from any points with higher local density. For each data point I, dpclust calculates two quantities: its local density rho sub I, measured using a Gaussian or cutoff kernel, and its distance delta sub I, defined as the minimum distance from point I to any point with a higher local density. By plotting delta sub I against rho sub I on a two-dimensional decision graph, cluster centers emerge clearly as points exhibiting both high local density rho and exceptionally large distance delta to higher density points. Once cluster centers are identified on the decision graph, remaining points are assigned to the same cluster as their nearest neighbor of higher density in a single fastpass. To evaluate clustering performance with maximum statistical rigor, engineers synthesize both internal validation criteria and external information theoretic metrics. Among internal evaluation metrics, the Dunn index measures the ratio of the smallest distance between observations in different clusters to the largest intracluster distance, known as the cluster diameter. A high Dunn index indicates that clusters are compact and well separated. However, because the Dunn index relies on extreme minimum and maximum distances, it is sensitive to noise and outliers. To improve robustness, generalized Dunn indices replace point-to-point extrema with average pairwise cluster distances. Another valuable internal metric is the COP index, which evaluates the ratio of intracluster distance from data points to their cluster centroid over the minimum intercluster distance between centroids. Lower COP index scores indicate tighter, better separated clusters. When ground truth labels are available for validation subsets, information theoretic external metrics complement pair counting indices like the adjusted RAND index. Normalized mutual information, or NMI, measures the shared information between predicted cluster assignments and true class labels, normalized by the arithmetic, geometric, or minimum entropy of the label distributions. Variation of information, or SIX, measures the total entropy gain lost when moving from predicted clusters to true labels, calculating the sum of conditional entropies. A variation of information score of 0 represents perfect clustering alignment. To test cluster stability empirically, software architectures implement consensus clustering and bootstrapping. Consensus clustering runs an algorithm multiple times across perturbed subsamples or different hyperparameter configurations, constructing an n-by-n consensus matrix that records how frequently pairs of points fall into the same cluster. A sharp consensus matrix with entry values close to 0 or 1 indicates stable, unambiguous cluster boundaries. To deepen our mathematical understanding of principal component analysis, let us walk through the explicit proof of equivalence between singular value decomposition and covariance matrix eigenvalue decomposition. Let X be an n by d mean-centered data matrix. The sample covariance matrix S is calculated as 1 divided by n minus 1 times X transpose times X. Applying singular value decomposition to X factorizes the matrix as U times sigma times V transpose, where U is an n by n orthogonal matrix of left singular vectors, sigma is an n by d diagonal matrix of non-negative singular values sigma sub I, and V is a d by d orthogonal matrix of right singular vectors. Substituting the SVD factorization of X into the covariance matrix equation yields S equals 1 divided by n minus 1 times the quantity V times sigma transpose times U transpose, multiplied by U times sigma times V transpose. Because U is an orthogonal matrix, U transpose times U equals the identity matrix. The expression simplifies to S equals V times the quantity sigma squared divided by n minus 1, multiplied by V transpose. Multiplying both sides of this equation on the right by matrix V yields S times V equals V times the quantity sigma squared divided by n minus 1. Comparing this matrix equation to the classic eigenvector equation S times W equals lambda times W reveals a fundamental identity. The right singular vectors V of the data matrix X are the exact eigenvectors of its sample covariance matrix S, and each eigenvalue lambda sub I equals the squared singular value sigma sub I squared divided by n minus 1. For massive out-of-core matrices that exceed RAM, systems use randomized PCA, such as the Hawko-Martenson-Trop algorithm. Randomized PCA multiplies the data matrix by a random Gaussian projection matrix to construct a low-dimensional sample subspace, applies QR factorization to form an orthonormal basis, and computes SVD on the reduced matrix in sublinear time. When data matrices contain sparse corruptions or impulse noise, engineers use robust PCA, or RPCA. Robust PCA decomposes data matrix X into the sum of a low-rank matrix L capturing true structural variance, and a sparse noise matrix S, optimizing a convex combination of nuclear norm and L1 norm penalties via principal component pursuit. To master nonlinear manifold learning, engineers must understand the exact force calculations and mathematical approximations that power t-SNE and UMAP. In t-SNE, the objective function is the Kullback-Leibler divergence between high-dimensional joint probabilities P and low-dimensional student T probabilities Q. The gradient of the KL divergence with respect to the low-dimensional point vector Y sub I acts as a system of physical forces. An attractive force pulling points together proportional to P sub ij times Q sub ij inverse, and a repulsive force pushing points apart proportional to Q sub ij squared. To accelerate gradient calculations from naive big O of n squared complexity down to big O of n log n, Barnes-Hutt t-SNE constructs a quadtree in 2 dimensions or an octree in 3 dimensions. For each data point, Barnes-Hutt checks whether a tree node is sufficiently far away by comparing the node's spatial width to its distance from the point. If the ratio is below a theta threshold, typically 0.5, The algorithm treats all points inside the node as a single distance center of mass, approximating repulsive forces using multipole expansions. For scaling to millions of data points, fast Fourier transform accelerated t-SNE, or FIT-SNE, interpolates repulsive forces onto an equispace spatial grid, evaluating convolution sums using fast Fourier transforms to achieve true linear big O of n scaling. In UMAP, manifold learning is grounded in Riemannian geometry and algebraic topology. UMAP models local manifold spaces as fuzzy simplicial sets using Čech and Vietoris-Rips complexes. In a simplicial complex, data points represent zero samplices, pairwise connections represent one samplices, and filled triangles represent two samplices. By computing fuzzy membership strength across high-dimensional samplices, UMAP constructs a continuous topological representation of the data manifold. Low-dimensional layout optimization minimizes fuzzy set cross-entropy, preserving both local cluster boundaries and global macroscale manifold topology. To understand neural nonlinear dimensionality reduction deeply, let us derive the evidence lower bound, or ELBO, loss function of variational autoencoders in continuous spoken prose. In a variational autoencoder, we observe an input vector x and assume it is generated by a latent variable z sampled from a prior probability distribution p of z. We want to maximize the marginal log likelihood of the observed data, log of p of x. However, calculating the true marginal log likelihood requires integrating p of x given z times p of z over all possible latent vectors z, an integral that is computationally intractable for complex neural networks. To resolve this intractability, variational autoencoders introduce an inference network, or encoder, q of z given x, to approximate the true posterior distribution p of z given x. Using Jensen's inequality and Bayes' rule, we express the marginal log likelihood log of p of x as the sum of two terms, the evidence lower bound, or ELBO, and the Kullback-Leibler divergence between the approximate posterior q of z given x and the true posterior p of z given x. Because the KL divergence is strictly non-negative, the ELBO serves as a guaranteed mathematical lower bound on the true marginal log likelihood of the data. Maximizing the ELBO maximizes data likelihood while pulling the approximate posterior toward the true posterior. The evidence lower bound breaks down into two distinct loss terms. The reconstruction expectation term, which measures the expected log likelihood of reconstructing input x from latent code z under decoder p of x given z, and the Kullback-Leibler regularization term, which measures the divergence between encoder posterior q of z given x and standard Gaussian prior p of z. To enforce disentangled latent representations, where individual latent dimensions correspond to isolated, independent physical attributes, engineers use beta VAES. A beta VAE scales the KL divergence loss penalty by a hyperparameter coefficient beta. Setting beta greater than 1 forces latent dimensions to become statistically independent, discovering interpretable disentangled factors of variation. For discrete latent spaces, vector quantized VAEs, or VQVAES, replace continuous Gaussian latent distributions with discrete codebook vectors, utilizing vector quantization to represent complex discrete structures. To design production-grade clustering pipelines, system engineers must master vector database indexing architectures and low-latency inference pathways. In real-time enterprise AI applications, such as semantic vector search or online recommendation systems, inference services must assign incoming query vectors to their nearest cluster centroids or item embeddings within sub-millisecond latency budgets. Scanning millions of high-dimensional vectors linearly using brute force distance calculations requires big O of n times d operations, introducing unacceptable latency spikes. Production architectures solve this bottleneck by deploying specialized vector databases, such as FAISS, HNSLib, Milvus, and Ctrant, that build approximate nearest neighbor graph indices over high-dimensional spaces. The dominant indexing architecture is Hierarchical Navigable Small World Graphs, or HNSW. HNSW constructs a multi-layer graph hierarchy over vector embeddings, inspired by probabilistic skip-list data structures. The top layer contains a sparse graph with long-range links between distant vector clusters, allowing fast course navigation across feature space. Middle layers contain moderately dense graphs, while the bottom layer contains a dense graph connecting immediate spatial neighbors. When an online query vector arrives, the search algorithm begins at an entry point on the top layer, greedily traversing edges to find the closest node. It then drops down to the corresponding node on the layer below, repeating the greedy search. This multi-layer navigation converges to the exact or near-exact nearest neighbor in logarithmic time complexity, big O of log n. Another indexing framework is inverted file indexing with product quantization, or IVFPQ. IVFPQ partitions feature space into k-Voronoi cells using k-means, constructing an inverted file index. It then applies product quantization, breaking high-dimensional vectors into smaller subvectors, clustering subvector spaces, and replacing subvectors with short byte codes. Pairwise distances are computed instantly via pre-computed lookup tables, reducing memory consumption by 90% while accelerating query throughput. To expand our enterprise customer segmentation case study, let us analyze advanced RFMT feature engineering, survival analysis integration, and customer transition matrices. In modern subscription and e-commerce platforms, customer behavior evolves across distinct lifecycle stages. Augmenting the classical RFM framework with account tenure, forming RFMT, captures customer loyalty trajectories over time. Tenure measures total account age in days, allowing models to distinguish newly acquired active buyers from long-term loyal power users. To model customer churn dynamics probabilistically, engineers integrate survival analysis with clustering. By fitting Kaplan-Meier survival curves and Cox proportional hazards models within each discovered customer segment, the system estimates the expected remaining lifetime value and churn hazard rate for individual customer accounts. Furthermore, production segmentation engines track Markov chain cluster transition matrices over consecutive time windows. A cluster transition matrix is a k-by-k probability matrix where entry p sub ij represents the empirical probability that a customer belonging to segment I in the current quarter transitions to segment j in the subsequent quarter. Analyzing transition matrix probabilities provides immense predictive power. If a customer in segment 0 VIP power buyers exhibits a surge in transition probability towards segment 1, at-risk candidates, the automated marketing system triggers proactive retention offers weeks before churn occurs, preserving enterprise revenue streams. To deepen our understanding of high-dimensional geometry, let us explore topological data analysis and the hubness problem. In high-dimensional feature spaces, distance concentration is accompanied by another severe pathology known as the hubness problem. Hubness refers to the phenomenon where a small number of data points, called hubs, emerge as nearest neighbors to disproportionately large numbers of other points across the dataset. Hubs distort spatial graph structures, causing nearest neighbor classifiers and graph clustering algorithms to produce biased, centralized cluster topologies. To reduce hubness, Engineers apply mutual nearest neighbor scaling or local distance normalization techniques to extract structural shape from high-dimensional noisy data without relying on rigid geometric metrics. Researchers use topological data analysis, or TDA. Topological data analysis applies persistent homology from algebraic topology to discover geometric invariants, such as connected components, loops, and hollow cavities, across multiple spatial scales. Persistent homology constructs a sequence of Vietoris-Rips simplicial complexes over data points across expanding distance thresholds epsilon. By tracking the birth and death of topological features, such as zero-dimensional connected components and one-dimensional holes, TDA outputs a persistence diagram or persistence barcode. Features that persist over a wide range of epsilon scales represent genuine structural topological phenomena, while short-lived features represent sampling noise, providing a coordinate-free approach to high-dimensional data analysis. To complete our hands-on cloud infrastructure project, let us detail the operational fault tolerance, failover architecture, and production deployment topology of our unsupervised machine intelligence engine. Our enterprise telemetry engine processes real-time metric streams from over 500,000 active server instances across global multi-region cloud clusters. The ingestion pipeline uses an Apache Kafka message bus deployed across 3 availability zones with a replication factor of 3, guaranteeing zero data loss during cloud node outages. The Spark Stream Processing Engine runs on Kubernetes, utilizing dynamic allocation to scale worker pods automatically based on Kafka queue depth. If a stream worker node fails, Kubernetes reprovisions the pod in seconds, resuming stream processing from stored Kafka offset checkpoints. For the real-time inference service, trained PCA projection matrices and k-mean centroid vectors are exported as ONNX format model artifacts and loaded into stateless C++ inference microservice containers deployed behind a global load balancer. The inference service maintains zero local state, allowing load balancers to scale container replicas horizontally to handle surges in telemetry traffic. And in-memory Redis cache stores recent node cluster assignments, satisfying sub-millisecond query SLAs for real-time auto-scaling and security orchestration services. Model retraining is automated via an Airflow DAG workflow that runs weekly or whenever population stability index alerts trigger. Retraining jobs fit new feature transformers and cluster centroids on fresh telemetry windows, run automated silhouette quality audits, and execute canary deployments, shifting traffic gradually to updated model containers while monitoring inference latency and reconstruction error. This complete production topology demonstrates how theoretical clustering concepts, dimensionality reduction math, vector databases, and fault-tolerant system engineering unite to form a resilient, self-healing machine intelligence platform. To expand our mathematical taxonomy of partitioning algorithms, we must examine spectral clustering. Spectral clustering approaches data partitioning from a graph-theoretic perspective, making zero assumptions about the geometric shape or convexity of clusters. In spectral clustering, the dataset is modeled as an undirected weighted graph, where each data point represents a node, and edges between nodes carry weights reflecting pairwise similarity, typically computed using a radial basis function Gaussian kernel. The algorithm constructs an n-by-n affinity matrix, A, storing these pairwise edge weights, and a diagonal degree matrix, D, where each diagonal entry represents the sum of edge weights connected to that specific node. The core mathematical foundation of spectral clustering is the graph Laplacian matrix, L, defined as the degree matrix D minus the affinity matrix A. engineers utilize two normalized variants of the graph Laplacian. The symmetric normalized Laplacian, calculated as the inverse square root of d times L times the inverse square root of d, and the random walk normalized Laplacian, calculated as the inverse of d times L. The mathematical power of the graph Laplacian lies in its spectral decomposition. The smallest eigenvalue of the graph Laplacian is always 0, and its corresponding eigenvector is a constant vector. The second smallest eigenvalue, known as the Fiedler value, and its corresponding eigenvector, known as the Fiedler vector, provide the optimal continuous relaxation for the discrete graph partitioning problem. The Fiedler vector solves the normalized cut, or n-cut, problem. It finds a bipartition of the graph that minimizes the total weight of edges severed between the two subgraphs divided by the total edge volume of each subgraph. This guarantees that spectral clustering cuts sparse bottleneck edges between dense graph communities without isolating single outlier nodes. To partition a dataset into k-clusters, spectral clustering computes the eigenvectors corresponding to the k smallest eigenvalues of the normalized graph Laplacian, forming an n by k matrix of spectral embeddings. It then normalizes each row to unit length and applies standard k-means clustering on the row vectors in this low-dimensional spectral space. By projecting raw data into the eigenspace of the graph Laplacian, spectral clustering unrolls complex nonlinear geometries, such as interlocking spirals or concentric rings, into linearly separable clusters where k-means succeeds effortlessly. Another foundational manifold learning paradigm is ISOMAP, which stands for isometric feature mapping. ISOMAP extends classical multidimensional scaling to nonlinear manifolds by replacing straight-line Euclidean distances with geodesic distances measured along the manifold surface. ISOMAP operates through a three-step pipeline. First, it constructs a k-nearest neighbor graph over all data points, setting edge weights equal to Euclidean distances between adjacent neighbors. Second, it estimates the geodesic distance between every pair of points in the dataset by computing the shortest path distance through the graph using Dijkstra's algorithm or the Floyd-Warshall algorithm. This constructs an n by n geodesic distance matrix that captures true distances along the curved manifold surface, avoiding shortcuts through empty ambient space. Third, ISOMAP applies classical multidimensional scaling, or MDS, to the geodesic distance matrix, performing eigenvalue decomposition on the centered inner product matrix to project data points into a low-dimensional Euclidean space that preserves pairwise geodesic distances. Similarly, locally linear embedding, or LLE, preserves local manifold geometry by assuming that every data point and its immediate neighbors lie on, or close to, a locally flat patch of the manifold. LLE first computes reconstruction weights that reconstruct each data point as a linear combination of its k-nearest neighbors, minimizing squared reconstruction error. Next, LLE fixes these reconstruction weights and computes low-dimensional coordinates that minimize the same reconstruction error in lower dimensions. Variants like Hessian LLE and modified LLE use higher-order differential operators to eliminate distortion in complex manifold geometries. When non-parametric Bayesian clustering is required, system architects utilize Dirichlet process mixture models, or DPMMs. Unlike standard k-means or finite Gaussian mixture models, which require pre-specifying the number of clusters k, a Dirichlet process mixture model assumes an infinite capacity mixture model where the number of active clusters grows logarithmically with the number of observations. Using the Chinese restaurant process or stick-breaking construction, a Dirichlet process mixture model assigns data points to existing clusters based on cluster popularity, while maintaining a non-zero probability of creating a brand new cluster whenever an observation deviates significantly from existing cluster distributions. This non-parametric flexibility allows the model to learn cluster counts automatically in streaming production data. To master vector database engineering and high-dimensional search architectures, system engineers must understand the mathematical mechanics of asymmetric distance computation, SIMD hardware acceleration, and statistical drift metrics. In product quantization within inverted file indexing pipelines, pairwise distance calculations are optimized using asymmetric distance computation, or ADC. In asymmetric distance computation, when a real-time unquantized query vector Q arrives, the system does not quantize Q. Instead, it computes the exact Euclidean or cosine distance between the raw continuous query vector Q and the quantized centroid codes of the dataset using precomputed lookup tables. Because the query vector remains unquantized while the stored database vectors are quantized into short byte codes, ADC eliminates quantization error on the query side, achieving significantly higher search recall than symmetric distance computation while maintaining gigabyte per second query throughput. To achieve sub-millisecond real-time search SLAs, vector databases leverage hardware-level single instruction multiple data, or SIMD vector instructions such as AVX512 and ARM Neon. SIMD instructions execute distance calculations across multiple vector dimensions concurrently in a single CPU instruction cycle, multiplying query throughput by orders of magnitude. In HNSW graph structures, the multilayer graph hierarchy is constructed probabilistically. When a new vector is inserted into the HNSW graph, its maximum layer height L is assigned randomly using an exponential probability distribution. L equals the floor of negative logarithm of a uniform random variable between 0 and 1, multiplied by a scaling normalization factor m sub L. This guarantees that higher layers contain exponentially fewer nodes, preserving the skip list logarithmic search navigation property. Now let us examine the mathematical formulation of statistical drift metrics used in production machine learning monitoring engines. To monitor feature distribution drift quantitatively, production monitoring pipelines track the Population Stability Index, or PSI, and the Wasserstein distance. The Population Stability Index measures the shift between a baseline reference probability distribution B and an actual target probability distribution T across discretized feature bins. The PSI formula sums across all bins the quantity actual percentage minus expected percentage, multiplied by the natural logarithm of the actual percentage divided by the expected percentage. A PSI score below 0.1 indicates zero significant distribution shift, confirming that the current model remains valid. A PSI score between 0.1 and 0.25 signals moderate population drift, requiring close monitoring. A PSI score exceeding 0.25 represents severe population drift, triggering automated model retraining DAGs. For continuous unbinned feature distributions, systems measure the Wasserstein distance, also known as the Earth mover's distance. The first Wasserstein distance measures the minimum work required to transform one probability distribution into another, calculated as the integral of the absolute difference between their cumulative distribution functions. Complementing Wasserstein distance, systems track Jensen-Shannon divergence, a symmetric, bounded variant of Kullback-Leibler divergence. Jensen-Shannon divergence ranges between 0 for identical distributions and 1 for completely disjoint distributions. By combining HNSW vector database indexing, SIMD hardware acceleration, asymmetric distance computation, and statistical drift tracking via PSI, Wasserstein distance, and Jensen-Shannon divergence, software engineers build bulletproof, real-time unsupervised machine learning systems that maintain peak accuracy and low latency performance across enterprise production lifecycles. To complete our comprehensive exploration of unsupervised dimensionality reduction and clustering architectures, we examine non-negative matrix factorization, latent Dirichlet allocation, and deep clustering architectures. Non-negative matrix factorization, or NMF, is a linear matrix decomposition technique designed specifically for non-negative feature matrices, such as image pixel intensities, term document count matrices, or audio spectrograms. Given a non-negative n by d matrix X, NMF factorizes X into the product of two non-negative matrices, an n by k basis matrix W and a k by d coefficient matrix H, where k is significantly smaller than d. Unlike PCA, which allows negative entry values and orthogonal axes, NMF enforces a non-negativity constraint on all entries in W and H. This non-negativity constraint forces NMF to learn an additive, parts-based representation. In image processing, NMF isolates localized facial features like eyes, noses, and mouths as individual basis components. In text processing, NMF extracts non-overlapping topic distributions. NMF optimization minimizes Frobenius norm reconstruction loss or Kullback-Leibler divergence using multiplicative update rules. For probabilistic topic modeling over discrete document collections, latent Dirichlet allocation, or LDA, provides a Bayesian generative framework. LDA models each document as a probabilistic mixture over a set of latent topics, and each topic as a multinomial distribution over vocabulary words, using Dirichlet prior distributions. In modern deep learning, deep clustering architectures unify feature learning and cluster optimization into an end-to-end differentiable neural network pipeline. Traditional two-stage pipelines, first running an autoencoder to extract latent features and subsequently running k-means on the static embeddings, suffer from a fundamental disconnect. The autoencoder optimizes reconstruction loss, which does not necessarily align with cluster separability. Deep embedding clustering, or DEC, resolves this by joint optimization. DEC first pre-trains a deep autoencoder to initialize a smooth latent space, discards the decoder, and attaches a soft cluster assignment layer using student t-distributions to measure similarity between latent vectors and cluster centroids. DEC optimizes a target distribution that sharpens soft cluster assignments using a Kullback-Leibler divergence loss, pulling latent representations closer to cluster centroids while pushing centroids apart. Improved deep embedding clustering, or IDUC, retains the decoder network during joint optimization, minimizing a weighted combination of reconstruction loss and clustering KL divergence. This dual loss prevents the neural network from distorting latent space geometry, learning sharp, cluster-friendly feature representations. For outlier scoring in density hierarchies, DBSCAN provides the GLOSH metric, standing for Global Local Outlier Score from Hierarchies. GLOSH measures the relative density of a point compared to the maximum density of the cluster hierarchy it belongs to, outputting a continuous outlier score between 0 and 1. GLOSH provides robust, multi-scale outlier detection across varying density clusters. By synthesizing classical matrix factorizations like NMF and LDA with modern deep embedding clustering, IDUC, and GLOSH outlier metrics, software engineers build versatile machine learning systems capable of mastering complex continuous, discrete, and deep structural manifolds. To complete our technical toolkit, we analyze self-organizing maps, biclustering paradigms, and contrastive representation learning. Self-organizing maps, or SOMs, also known as Cajonan maps, are an unsupervised neural network model that projects high-dimensional feature vectors onto a low-dimensional grid of neurons while preserving spatial topological relationships. During competitive training, an incoming vector identifies its best matching unit neuron in the grid. The best matching unit and its neighboring grid neurons adjust their weight vectors toward the input vector using a spatial neighborhood decay function. SOMs provide an intuitive visual bridge between clustering and topological manifold mapping. For multidimensional matrices where rows and columns exhibit simultaneous correlation, such as gene expression data or document word frequency matrices, systems use biclustering and co-clustering algorithms. Spectral biclustering applies singular value decomposition to normalized data matrices, discovering checkerboard patterns of co-clustered rows and columns. Information theoretic co-clustering optimizes mutual information between row and column discrete distributions, grouping features and observations simultaneously. Finally, in modern deep unsupervised learning, contrastive representation learning, such as SimCLR and momentum contrast or MoCo, has emerged as the premier nonlinear dimensionality reduction front-end for unlabeled visual and sequence data. Contrastive learning creates synthetic multiview pairs by applying random data augmentations to an unlabeled input, such as cropping, color jittering, or random masking. It passes the augmented views through a deep convolutional or vision transformer backbone to extract embedding vectors. The contrastive loss function, known as InfoNCE loss, maximizes cosine similarity between positive augmented pairs derived from the same original image, while minimizing similarity across negative pairs derived from different images in the mini-batch. InfoNCE loss acts like a temperature-scaled cross-entropy loss over normalized feature embeddings. By training deep neural backbones to become invariant to irrelevant data augmentations while discriminating between distinct data samples, contrastive learning learns rich, nonlinear continuous representations that outperform classic manual feature engineering. Downstream clustering algorithms like k-means or DBSCAN, when fitted directly on contrastive embedding vectors, discover highly pure, semantically meaningful clusters. This completes our exhaustive tour of unsupervised learning. From centroid partitioning, hierarchical trees, and density-based graphs to linear PCA, nonlinear t-SNE, UMAP, autoencoders, spectral graph Laplacians, vector database indices, and contrastive neural representations, you possess the definitive staff engineer blueprint for building state-of-the-art unsupervised machine intelligence platforms. In conclusion, long-form technical mastery requires embracing the full spectrum of unsupervised methods. Whether you are partitioning high-throughput financial logs using mini-batch k-means, constructing multi-tiered biological taxonomies with Ward's agglomerative trees, isolating non-spherical spatial telemetry using DBSCAN and optics, compressing feature spaces via singular value decomposition in linear PCA, unrolling complex manifolds using t-SNE and UMAP, or training probabilistic variational autoencoders and contrastive neural representations, the core principles remain constant. You must normalize feature scales, select distance metrics aligned with domain geometry, validate cluster boundaries using silhouette and Davies-Bouldin metrics, index high-dimensional spaces with HNSW graphs, and track population stability index drift continuously in production. With these mental models and system engineering principles established, you are fully equipped to architect, deploy, and scale enterprise-grade unsupervised machine intelligence platforms.